Something went wrong 5.7 billion light-years from here. A black hole grew too large. It crossed a line written into the fabric of space-time itself. And instead of shutting down the galaxy it was supposed to regulate, it watched as new stars ignited at impossible rates, as cold gas poured inward where only heat should exist, as the rules of cosmic equilibrium simply stopped applying. The object is called Phoenix A, and it is not behaving. 100 billion times the mass of our Sun, an event horizon so vast it could swallow the distance from our star to Pluto 100 times over and still have room left inside, larger than Toen 618, larger than anything humanity has ever confirmed. A stupendously large black hole sitting at the center of the most X-ray-luminous galaxy cluster ever discovered, feeding at a rate that defies the Eddington limit, the theoretical speed cap on how fast a black hole can grow without tearing itself apart. Except this one did not tear apart. It just kept growing, and the galaxy around it did not die. It erupted. 800 new stars every year, birthed from gas that should have been blasted away by the black hole's radiation but instead fell inward, condensed and lit up. A failure of regulation so profound that astronomers are still struggling to explain how the system remains stable. Phoenix A does not fit our models. It should not have been able to form this quickly, this large, this early in cosmic history. And yet the data does not lie. The shadow is there. The mass is real. The stars are burning. So how does a black hole grow past the ceiling we thought existed? How does a cosmic executioner lose control of its own domain? And what does it mean when the largest object of its kind we have ever measured turns out to be the one breaking all the rules? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. There is a cluster of galaxies sitting 5-7 billion light-years from Earth that should not be doing what it is doing. Astronomers call it the Phoenix Cluster, and for the last decade it has been quietly breaking the rules, not bending them, breaking them, flat out ignoring the mechanisms that are supposed to govern how galaxies grow, how stars form, and how the universe keeps itself in check. And at the center of this rebel cluster, buried inside its largest galaxy, there is a black hole so massive that its very existence forces physicists to admit something deeply uncomfortable. Either our models are incomplete, or the early universe was building things we still do not understand. Let's start with what makes the Phoenix Cluster strange in the first place. Because before you can appreciate the monster sitting at its core, you need to understand the environment that monster is supposedly controlling. Galaxy clusters are the largest gravitationally bound structures in the universe. They are cities of galaxies, hundreds or thousands of them packed into a region of space spanning millions of light years. Between those galaxies floats an ocean of hot gas, most of it hydrogen and helium, heated to tens of millions of degrees by the cluster's gravitational collapse. That gas glows in X-rays. The hotter and denser the gas, the brighter the X-ray emission. That is how we find these clusters. We point X-ray telescopes at the sky and look for the bright spots. The Phoenix Cluster showed up on X-ray surveys as something that should not have been possible. It is one of the most X-ray-luminous galaxy clusters ever discovered. Not just bright, 7 times brighter than a typical massive cluster. That kind of luminosity means the gas inside it is extraordinarily hot and extraordinarily dense. Under normal circumstances, that gas should be cooling. When gas cools, it loses pressure. When it loses pressure, gravity takes over. The gas falls inward toward the center of the cluster, piling up around the central galaxy, condensing into clouds, collapsing into stars, lots of stars. Entire generations of them, born in rapid succession, lighting up the core of the cluster like a fireworks display that never stops. That process is called a cooling flow, and it was one of the dominant ideas in astrophysics for decades. Astronomers expected massive galaxy clusters to be star factories, churning out hundreds or even thousands of solar masses worth of new stars every year. The math said so. The observations of hot gas said so. Everything pointed toward runaway star formation at the hearts of the biggest clusters in the universe. Then they looked closer and found almost nothing. Most galaxy clusters were not forming stars at anything close to the predicted rates. They were forming a handful per year at most, sometimes none at all. The cooling flows were not flowing. It took years to figure out why. The answer turned out to be sitting right in the middle of every cluster that was not forming stars. A supermassive black hole. Not just any black hole, an active one. A black hole that was feeding, pulling in gas, heating it to millions of degrees in an accretion disk, and then launching enormous jets of energy outward into the surrounding space. Those jets, driven by magnetic fields twisted around the black hole's spin, pump energy back into the cluster gas. They heat it, they stir it, they blow bubbles in it the size of entire galaxies. And in doing so, they shut down the cooling flow before it ever gets started. This process is called feedback, and it is one of the most important regulatory mechanisms in the universe. Without it, every massive galaxy at the center of a cluster would be a monster, bloated with stars, devouring gas at a rate that would exhaust the cluster's supply in a few 100 million years. With feedback, the black hole acts like a thermostat. When the gas cools and starts to fall inward, the black hole eats a little bit of it, fires up its jets, and heats the gas back up. The cycle repeats. The gas never fully cools, the stars never fully ignite. The system stays in balance. For more than 2 decades, this picture has been the foundation of how astronomers understand galaxy cluster evolution. The Phoenix cluster does not care about that picture. It is forming stars at a rate of roughly 800 solar masses per year. Not a handful, not a trickle, 800 times the mass of our Sun every single year. That is more than 200 times the star formation rate of the Milky Way. It is one of the highest star formation rates ever measured in a galaxy cluster. The cooling flow that was supposed to have been shut down by feedback is running at full throttle. The gas is cooling, the gas is falling, the stars are igniting, and the black hole at the center, the thing that is supposed to be regulating all of this, is just sitting there, watching. Except it is not just sitting there, it is feeding, actively, violently, growing at a rate of roughly 60 solar masses per year. That is not a typo. This black hole is gaining the equivalent of 60 suns worth of mass every single year. It is one of the fastest growing supermassive black holes in the local universe. And yet, despite that furious feeding, despite the energy it should be pumping back into the cluster, the cooling flow has not stopped. The stars have not stopped forming. Something went seriously wrong, or seriously right, depending on how you look at it. Either the black hole is not powerful enough to stop the infall, which would contradict decades of feedback theory, or the cluster has so much gas pouring inward that even a black hole this massive cannot keep up. Both options are uncomfortable. Now we come to the black hole itself. Phoenix A star. That is the name astronomers have given to the supermassive black hole sitting at the heart of the Phoenix cluster's central galaxy. And when I say supermassive, I need you to understand that the word has lost all meaning at this scale. Most supermassive black holes weigh somewhere between a few million and a few billion times the mass of the Sun. Sagittarius A star, The black hole at the center of our Milky Way weighs about 4 million solar masses. That is a typical middleweight. On the heavy end, you have objects like the black hole in Messier 87, the one we managed to photograph with the Event Horizon Telescope back in 2019. That one weighs about 5 billion solar masses, enormous by any human measure, still within the range of what models predicted. Then there is TON 618. For years, TON 618 held the title of the most massive black hole ever confirmed. Sitting roughly 4 billion light-years away, it weighs in at approximately 66 billion solar masses. It is a quasar, which means it is actively feeding, and the light from its accretion disk outshines entire galaxies. Its event horizon stretches more than 1,300 astronomical units from its center. You could fit dozens of solar systems across that span. For a long time, TON 618 was the ceiling, the upper limit of what a black hole could realistically become. Theoretical models suggested that black holes much larger than 50 billion solar masses should not be able to form. The physics of accretion, the availability of gas, the time required to grow that large. All of it pointed toward a natural cutoff somewhere in that range. Phoenix A star weighs roughly 100 billion solar masses, not 50 billion, not 66 billion, 100 billion, 100,000 million times the mass of our Sun. It is not just larger than TON 618, it is 50% larger. It has doubled what physicists thought was the upper limit for black hole mass, and it is sitting in a cluster that is actively feeding it, funneling hundreds of solar masses of gas inward every year, while simultaneously forming stars at a rate that should have been impossible if the black hole were doing its job. Let me give you a sense of what 100 billion solar masses actually means. The event horizon of Phoenix A star, the boundary beyond which nothing can escape, has a diameter of roughly 590 billion kilometers. That is about 3,900 astronomical units. For context, Pluto orbits the Sun at about 40 astronomical units. The event horizon of this black hole is nearly 100 times the distance from the Sun to Pluto. If you tried to walk across it at a steady pace of 5 kilometers per hour, it would take you more than 13 million years to get from one side to the other. A beam of light traveling at 300,000 kilometers per second, the fastest thing in the universe, would take just over 22 days to cross the diameter. Not 22 hours, 22 days. And if you account for the circumference, the time stretches to more than 71 days. This is not a black hole in the sense that most people picture one. It is not a small, dense point. It is a region of space so warped that an entire solar system could vanish into it without ever touching the sides. You could drop Jupiter into Phoenix A star, and it would be like tossing a pebble into the Pacific Ocean. You could drop 1,000 Jupiters, and the black hole would not notice. The scale is so far removed from anything in our daily experience that the numbers stop meaning anything. Your brain sees 100 billion and treats it the same as a million or a trillion. They all just become big. But this is not abstractly big. This is an object massive enough that if it replaced the Sun, its event horizon would swallow everything out past the Kuiper belt and keep going. And here is the truly unsettling part. We do not know how it got this big. The problem is time. Black holes grow in two ways. They eat matter and they merge with other black holes. Both processes take time. A black hole that feeds as efficiently as physics allows, consuming gas at the maximum rate without blowing itself apart, doubles in mass roughly every 50 million years. That rate is called the Eddington limit, and it is set by the balance between gravity pulling matter inward and radiation pressure from the infalling matter pushing it back out. If a black hole tries to eat faster than the Eddington limit, the radiation becomes so intense that it blows away the surrounding gas. The black hole chokes on its own meal. Start with a black hole that forms from the collapse of a massive star. Call it 100 solar masses, which is generous. That is one of the largest stellar mass black holes we know of. Let it grow at the Eddington limit for 13.8 billion years, the entire age of the universe. You end up with a black hole weighing somewhere in the neighborhood of a few billion solar masses. Not 100 billion, a few billion. To reach 100 billion solar masses in the time available, you need to start with something much heavier, or you need the black hole to grow faster than the Eddington limit allows, or you need it to merge with other supermassive black holes over and over again in rapid succession. All three scenarios have problems. The first option requires the existence of seed black holes in the early universe weighing tens of thousands or even millions of solar masses. These are not the remnants of dying stars, they are something else. Maybe they formed from the direct collapse of enormous primordial gas clouds in the first few 100 million years after the Big Bang. Clouds so massive and so dense that they skipped the star formation process entirely and collapsed straight into black holes. This is called direct collapse, and it is one of the leading ideas for how the first supermassive black holes came to exist. The trouble is, we have never seen one. We have models, we have simulations, we do not have observations. The James Webb Space Telescope is looking, but so far nothing definitive. The second option, super Eddington accretion, requires the black hole to somehow bypass the radiation pressure problem. Maybe the gas is falling in so fast and from so many directions at once that the radiation cannot escape efficiently. Maybe the black hole is spinning so rapidly that it drags space-time around with it, changing the geometry of the accretion flow in ways that allow more matter to fall in. There is some evidence that this can happen in short bursts. Whether it can be sustained for billions of years is another question. The third option, repeated mergers, sounds plausible until you run the numbers. Supermassive black holes do merge. We know that because we have detected the gravitational waves from smaller black hole collisions, and we expect the same process to happen at larger scales. But mergers are rare. Two galaxies have to collide. Their central black holes have to sink toward the center of the merged galaxy. They have to lose enough orbital energy to actually meet, and then they have to merge. Each step takes tens or hundreds of millions of years. To build a 100 billion solar mass black hole from mergers alone, you would need a long series of perfectly timed collisions, each one involving black holes that were already enormous. It is not impossible. It is just statistically unlikely. And yet here it is, Phoenix A star, sitting in a cluster that is 7 billion light-years away, meaning we are seeing it as it existed 7 billion years ago. The universe at that point was already more than 8 billion years old. Plenty of time for black holes to grow, but not necessarily enough time for one to reach 100 billion solar masses unless something unusual was happening. Unless the Phoenix cluster, even back then, was an outlier. A place where the rules bent just enough to allow something this extreme to form. The discovery of Phoenix A star was not a single eureka moment. It was a slow accumulation of data from multiple telescopes over several years. X-ray observations from the Chandra X Ray Observatory identified the Phoenix cluster as an extreme system. Optical and infrared observations from Hubble and ground-based telescopes mapped the central galaxy and measured the motions of stars near its core. Those motions, the speeds at which stars orbit the galactic center, are directly tied to the mass of the black hole sitting there. The faster the stars move, the more mass must be pulling on them. When astronomers plugged the numbers into their models, the result was unmistakable. The black hole at the center of the Phoenix cluster's brightest galaxy was not just large, it was off the charts. The scientific community did not immediately embrace the result. Extraordinary claims require extraordinary evidence, and a black hole weighing 100 billion solar masses is about as extraordinary as it gets. Some researchers questioned whether the mass estimates were reliable. Maybe the stars were being influenced by something other than the black hole. Maybe there was a dense cluster of dark matter near the center skewing the measurements. Maybe the models themselves were making assumptions that did not hold at this scale. Those objections are still being worked through. But the more data that comes in, the harder it becomes to argue that Phoenix A star is anything other than what it appears to be. A black hole that has broken the theoretical ceiling and is still growing. Here is what keeps me awake. Phoenix A star is not a relic. It is not a dormant fossil from the early universe quietly coasting through space. It is active. It is feeding. It is pulling in 60 solar masses of gas every single year. At that rate, it will gain another billion solar masses in less than 17 million years. That is a blink in cosmic time, and nothing in the current environment of the Phoenix cluster suggests it is going to stop. The cooling flow is still pouring gas inward. The stars are still forming. The black hole is still eating. The feedback mechanism that is supposed to regulate all of this, the jets, the heating, the pressure, all of it is there. We can see the signatures in the X-ray data, but it is not strong enough, or it is not fast enough, or the cluster has so much gas that even a black hole this powerful cannot throttle the inflow. That brings us to the real question, not how did Phoenix A star get this big? That is a question about the past. The real question is what happens next. Because if feedback cannot stop the cooling flow in the Phoenix cluster, if a 100 billion solar mass black hole feeding at 60 solar masses per year is not enough to shut down star formation, then either Phoenix A star is going to keep growing until it does become strong enough, or the cluster is going to exhaust its gas supply in a few 100 million years and go quiet. Either way, we are watching something that should not be happening according to the models. We are watching a system that has slipped outside the boundaries of cosmic regulation, and the fact that it exists at all means there are probably others. We just have not found them yet. The shadows this thing casts are not metaphorical. They are real, measurable, and they stretch across distances that make interstellar space look small. The shadows this thing casts are not metaphorical. They are real, measurable, and they stretch across distances that make interstellar space look small. When astronomers talk about the shadow of a black hole, they are not speaking poetically. They are describing an actual observable phenomenon, a silhouette carved into the fabric of space itself. And if we could point the Event Horizon Telescope at Phoenix A star with the same precision we used to photograph M87 star, the shadow we would see would redefine what the word enormous means. To understand what that shadow represents, you need to start with what a black hole actually does to light. A black hole does not pull light toward it the way gravity pulls on a ball. Gravity does not reach out and grab. What a black hole does is warp the space around it so severely that light, which always travels in straight lines through space, finds that the straight line it is following curves inward. The closer light gets to the black hole, the more extreme that curvature becomes. At a certain distance, the curvature becomes so steep that even light aimed directly away from the black hole curves back toward it. That distance is the event horizon. Cross it and every possible forward direction in space-time points inward. There is no trajectory, no velocity, no force in the universe that can reverse that geometry. You are not being pulled. The universe itself has tilted beneath you, and down is the only direction left. But before you reach the event horizon, there is another boundary, a wider one, the photon sphere. This is the distance at which light can orbit the black hole, traveling in a circle around it without falling in or escaping. Any light that crosses inward past the photon sphere either falls into the event horizon or escapes outward. That outward light, bent and distorted by its near miss with the black hole, is what creates the shadow. If you could somehow place a glowing screen behind a black hole and look at it from the other side, you would see a perfect dark circle where the black hole sits. Not because the black hole itself is visible, it is not, but because all the light that would have reached your eyes from that direction has been swallowed or bent away. The shadow is not the event horizon, it is larger, roughly 2.5 times larger, depending on whether the black hole is spinning. The shadow is the silhouette of the photon sphere, the edge of the zone where light loses its fight to escape. In April 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole. The target was M87 star, the supermassive black hole at the center of the galaxy Messier 87, sitting roughly 55 million light-years from Earth. The image showed a bright ring of light surrounding a dark circle. The bright ring was the accretion disk, gas spiraling inward at nearly the speed of light, heated to billions of degrees, glowing in radio wavelengths. The dark circle was the shadow. The size of that shadow was about 40 billion kilometers across. That is roughly 270 times the distance from the Earth to the Sun. For a black hole weighing 5 billion solar masses, that is exactly the size the shadow should be. The observation matched the predictions of general relativity so precisely that it effectively closed the door on alternative theories of gravity at that scale. Now scale that up to Phoenix A star. Phoenix A star weighs roughly 100 billion solar masses. That is about 15 times heavier than M87 star. The event horizon of a black hole grows linearly with mass. Double the mass, double the radius, triple the mass, triple the radius. Phoenix A star is 15 times more massive than M87 star. So its event horizon is 15 times larger. The event horizon diameter of Phoenix A star is approximately 590 billion kilometers. The shadow, being roughly 5 times the size of the event horizon, would stretch to about 1.5 trillion kilometers across. That is just under 10,000 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun. The shadow of Phoenix A star is 10,000 times that distance. Let me put that in terms that might land a little harder. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object from Earth. As of 2025, it is roughly 160 astronomical units away, well beyond the orbit of Pluto, coasting through interstellar space. It has been traveling for nearly 50 years. At its current speed, it would take Voyager 1 another 300 years to reach the edge of the Oort cloud, the outer boundary of objects still loosely bound to our Sun's gravity. The Oort cloud is thought to extend out to about 100,000 astronomical units. The shadow of Phoenix A star, at 10,000 astronomical units, would stretch 1/10 of the way to the outer edge of our solar system's gravitational influence. If you placed Phoenix A star where our Sun is, its shadow would engulf everything. The Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, the Kuiper belt, and everything inward of the inner Oort cloud, gone. All of it sitting inside a region of space from which light cannot escape. The word shadow does not do it justice. This is not a dark spot on a wall. This is a hole in reality large enough to swallow star systems whole without them ever brushing the sides. And here is the part that makes it worse. You would not see it coming. If you were somehow piloting a spacecraft toward Phoenix A star from a distance of a few light years, you would see the stars around it behaving strangely. Their light would bend and distort into arcs and rings as space-time warped in the black hole's vicinity. But you would not see the black hole itself. There would be no glowing marker, no boundary sign, just a region of space where stars that should be visible are not. And if you kept flying toward it, there would come a point where you crossed the event horizon, and you would not feel it. There would be no jolt, no sensation of passing through. The geometry of space-time inside the horizon is so smooth, so continuous with the geometry outside, that locally in your immediate vicinity, everything would seem normal. You would still see stars ahead of you. You would still see your instruments functioning. You would still feel weightless, coasting through space the way you always had. But you would be doomed. Not because something reached out and grabbed you, because the shape of the universe around you had changed in a way that made returning impossible. The concept of stupendously large black holes, or slabs, is relatively new. The term was proposed in 2017 by British cosmologist Bernard Carr and his colleagues as a way to describe black holes that exceed 10 billion solar masses. For most of the history of black hole research, that mass range was considered theoretical. Sure, the equations allowed for black holes that heavy, but finding one was another matter. Most supermassive black holes sit comfortably in the range of a few million to a few billion solar masses, even the heaviest ones discovered before Phoenix A star. Objects like TOE N618 and Holmberg 15A star were pushing but not breaking the 100 billion solar mass threshold. Phoenix A star broke it, and in doing so, it became the first confirmed member of the slab category. Priyamvada Natarajan, an astrophysicist at Yale University and one of the leading researchers studying the formation of supermassive black holes, has been tracking this class of objects for years. She has argued that slabs are not just scaled-up versions of regular supermassive black holes. They represent a fundamentally different growth pathway. In a 2024 paper, she noted that Phoenix A star is direct evidence that some black holes did not grow slowly through accretion and mergers. They formed from massive gas clouds that collapsed all at once in the early universe. These are called direct collapse black holes, and they would have started life already weighing hundreds of thousands or even millions of solar masses. From there, they had a head start. They could feed more efficiently. They could merge with other black holes without waiting billions of years for galaxies to collide. They could reach 100 billion solar masses in the time available. Barely. The problem with this idea is that we have never directly observed a direct collapse event. We have simulations showing that under the right conditions, a massive cloud of primordial hydrogen and helium, untouched by earlier generations of stars, could collapse without fragmenting into smaller pieces. Normally, gas clouds break apart as they collapse. Pockets of higher density form, each one becoming a seed for a star. But if the gas is hot enough and the cloud is rotating slowly enough, it can stay intact. The entire cloud collapses in one go, skipping the star formation step entirely, and the result is a black hole weighing tens of thousands of solar masses or more. This is not wild speculation. The physics is sound, but observing it requires catching a collapse in progress, or at the very least, finding a very young black hole in the early universe that is already far heavier than any star could produce. The James Webb Space Telescope is looking. So far, nothing definitive, But if Phoenix A star really did form this way, it is proof that the process happens. We just missed it by billions of years. The alternative explanation is mergers. Lots of them. Imagine two galaxies colliding. Each one has a supermassive black hole at its center. Over time, as the galaxies merge and their stars and gas intermingle, the two black holes sink toward the center of the new combined galaxy. They orbit each other, gradually losing energy to gravitational radiation and interactions with nearby stars. Eventually, they merge. The resulting black hole is heavier than either of the originals. Now repeat that process over and over. Every time the galaxy collides with another galaxy, the central black hole gains mass. After a dozen or more major mergers, you could, in theory, end up with something in the 100 billion solar mass range. This explanation has the advantage of being based on processes we know happen. Galaxies do collide. Black holes do merge. We have detected the gravitational waves from smaller black hole mergers, and we expect the same thing to happen at larger scales. The problem is timing. Mergers are slow. Even after two galaxies collide, it can take hundreds of millions of years for the black holes to actually meet. And not every collision produces a merger. If the galaxies pass by each other at the wrong angle, the black holes might just get flung off into space. If the merger does happen, the resulting black hole needs time to settle down before it can start feeding efficiently again. To build a 100 billion solar mass black hole through mergers alone, you need a perfect storm of conditions. The host galaxy needs to be in a dense environment where collisions are common. The black holes involved need to be already massive to begin with. The mergers need to happen in rapid succession, and all of this needs to occur within the first few billion years of the universe's history. It is possible, but statistically it is unlikely. Which means if Phoenix A star formed this way, it is an outlier among outliers, the product of a merger history so extreme that it should be one of a kind. Except we do not think it is. Here is something that does not get talked about enough. Phoenix A star is the largest black hole we have confirmed. It is not necessarily the largest black hole that exists. The universe is big, really big. There are hundreds of billions of galaxies, most of which we have never studied in detail. The odds that we just happen to find the single largest black hole on our first serious survey of the distant universe are not great. More likely, Phoenix A star is one of many slabs scattered throughout the cosmos. We just have not found the others yet. And if that is true, if there are more black holes out there in the 100 billion solar mass range or higher, then the models are not just slightly off. They are missing something fundamental about how black holes grow. There is another angle to this that makes the scale even harder to grasp. The mass of Phoenix A star is roughly 50% of the total stellar mass of its host galaxy. Read that again. Half the mass of all the stars in the galaxy is sitting inside the black hole at the center. In a typical galaxy, the central black hole weighs about 0.1% of the total stellar mass, maybe 1% in unusually massive galaxies. Phoenix A star is 50%. That is not a black hole sitting inside a galaxy. That is a galaxy built around a black hole. The black hole is not a feature of the system. It is the system. Everything else, the stars, the gas, the dark matter halo, all of it is just the scaffolding holding the black hole in place. If you could somehow stand on a planet orbiting a star near the center of the Phoenix galaxy, assuming such a planet could exist in that radiation-soaked environment, you would see a night sky unlike anything we experience on Earth. The sky would not be dark. The light from the accretion disk around Phoenix A star would dominate the view, a swirling ring of blue-white light so bright that it would cast shadows at night. If you were close enough, Within a few dozen light years of the black hole, the sky would not have individual stars. It would be a continuous glow, a haze of light from millions of stars packed so densely that they blur together. And at the center of it all, there would be nothing. Not a dark circle, because you would be inside the photon sphere. You would not be able to see the shadow, but you would see the geometry. The stars around you would appear to stretch and distort, pulled into arcs by the warping of space-time. If you looked directly away from the black hole, you would see a bright ring of stars compressed into a thin band. Look toward the black hole, and the stars would fan out, their light bent around the edges of your field of view. The sky itself would be a lens, and you would be looking through it. That is not hypothetical. That is what general relativity predicts. The math has been run. Simulations have been made. We know what the sky looks like near a black hole of this size. We just do not have anyone there to see it. And that is probably for the best, because the radiation environment near Phoenix A star would cook you down to your atoms long before you got close enough to appreciate the view. The accretion disk around a black hole this size is not just hot, it is a particle accelerator. Gas falling inward reaches a significant fraction of the speed of light. Magnetic fields twisted around the black hole's spin accelerate charged particles to energies that would make the Large Hadron Collider look like a toy. Those particles collide with photons, scattering them into X-rays and gamma rays. The entire region within a few light-years of the black hole is flooded with radiation intense enough to strip atoms apart. Any planet, any moon, any piece of rock or ice within that zone would be sterilized in seconds, and yet the black hole itself is perfectly calm. From the outside it looks violent, matter screaming inward, jets of plasma shooting outward at nearly light speed, radiation blazing in every direction. But the black hole itself, the event horizon, is the smoothest surface in the universe. No texture, no features, no hair, as physicists like to say, just a boundary defined by geometry. The only things that define a black hole are its mass, its spin, and its electric charge. Everything else, the composition of the matter that fell in, the history of how it grew, the temperature, the pressure, all of it is erased. The black hole remembers nothing. It is a delete button for information, and the larger it gets, the more it erases. Phoenix A star has erased a lot. 100 billion suns worth of matter has fallen across that event horizon over the last several billion years, all of it gone. Not destroyed in the sense of being broken apart, destroyed in the sense of being removed from the universe. The atoms that made up those stars, the photons they emitted, the gravitational waves they sent rippling through space-time, none of it can ever come back. It is sealed inside a region of space that has no future connection to the outside. And yet the black hole itself still affects the universe around it. Its gravity shapes the orbits of nearby stars. Its accretion disk pumps energy into the surrounding gas. Its jets blast through the intergalactic medium, carving cavities light years across. The black hole is gone from our universe in one sense, but in another sense, it has never been more present. That duality is what makes black holes so unsettling. They are absences that have weight, holes that have gravity, nothing that can still kill you. The universe does not offer many things that fit that description. Most objects in space are either there or they are not. Stars exist, planets exist. You can touch them, measure them, map them. Black holes exist in a different way. They are boundaries more than objects, edges of space-time that happen to be spherical. And when one of those edges is large enough to swallow a solar system without noticing, the human brain stops being able to process it. We do not have the machinery for it. Evolution built us to understand distances we can walk, weights we can lift, dangers we can see coming. A sphere of nothing 590 billion kilometers across, sitting 7 billion light-years away is not something our brains were designed to model. We can write the equations, we can run the simulations, we can point our telescopes and measure the numbers, but we cannot feel it. Not really. The scale is too large, the geometry is too strange, the consequences are too absolute. And that brings us to the edge of the real question. Phoenix A star is the largest black hole we have ever confirmed, but it is not the largest black hole the universe can make. There is no known upper limit. As long as there is gas to feed on, as long as there are other black holes to merge with, a black hole can keep growing, and Phoenix A star is still feeding. 60 solar masses per year. That is not a rounding error. That is a rate of growth that, if sustained, would add another billion solar masses in less than 17 million years. The black hole is still active. It is still pulling in matter. It is still getting heavier, and nothing in our current understanding suggests it is going to stop, which means in a few billion years, if the cluster does not run out of gas, Phoenix A star could be even larger, 110 billion solar masses, 120 billion. At some point, the numbers stop mattering. The scale has already broken our ability to conceptualize it. But the black hole does not care. It will keep eating until there is nothing left to eat. And when that day comes, when the last star in the Phoenix cluster goes dark and the last wisp of gas falls across the event horizon, Phoenix A star will still be there, a silent monument to gravity, a shadow cast by nothing, a hole in space that weighs more than most galaxies, waiting. There is a speed limit in the universe that has nothing to do with the speed of light. It is called the Eddington limit, and it governs how fast a black hole can eat, not how much it wants to eat, how much physics will allow it to eat before the meal fights back. For more than a century, this limit has been one of the bedrock principles of astrophysics. A hard constraint on how quickly massive objects can grow by pulling in gas and dust. It is named after Arthur Eddington, the British astrophysicist who first worked out the math in the 1920s while studying why stars do not collapse under their own gravity. What he discovered was that there is a point, a precise threshold, where the outward pressure of radiation becomes strong enough to balance the inward pull of gravity. Push past that point, and the radiation wins, the gas gets blown away, the feeding stops. For decades, this principle has explained why stars have maximum brightnesses, why accreting black holes have characteristic luminosities, and why supermassive black holes take billions of years to grow. It is one of the rules, and Phoenix A star appears to have broken it. Let me explain how the Eddington limit works, because this is not some abstract theoretical nicety. This is the mechanism that controls whether a black hole the size of Phoenix A star can even exist. Imagine a black hole sitting in the middle of a cloud of gas. Gravity pulls the gas inward. As the gas falls, it speeds up. As it speeds up, it heats up. By the time the gas gets close to the black hole, it is moving at a significant fraction of the speed of light, and it has been heated to millions of degrees. At those temperatures, atoms are ripped apart into ions and free electrons. The gas is no longer a gas in the normal sense. It is a plasma, a roiling soup of charged particles spiraling around the black hole in what we call an accretion disk. Now here is the problem. Hot plasma radiates a lot. The hotter it gets, the more energy it pumps out in the form of photons, X-rays, ultraviolet light, sometimes gamma rays. That radiation does not just sit there. Photons carry momentum. When a photon slams into an electron, It transfers some of that momentum, giving the electron a little kick. In normal circumstances, that kick is negligible. But when you have an accretion disk glowing with the energy of billions of suns, the cumulative effect of trillions upon trillions of photons slamming into electrons adds up. The radiation starts pushing back against the infalling gas. The closer the gas gets to the black hole, the stronger that push becomes. At a certain point, the outward radiation pressure exactly balances the inward gravitational pull. That point is the Eddington limit. If the black hole tries to pull in more gas, the radiation becomes so intense that it blows the gas away before it can fall in. The black hole chokes. The feeding rate maxes out. The formula for the Eddington limit is straightforward. The maximum luminosity a black hole can sustain is proportional to its mass. Specifically, the Eddington luminosity is roughly 33,000 times the mass of the object in solar masses, multiplied by the luminosity of the Sun. For a black hole weighing 1 million solar masses, the Eddington luminosity is about 33 billion times the brightness of our Sun. For a black hole weighing 100 billion solar masses, the Eddington luminosity is 3.3 quadrillion times the brightness of the Sun. That is an almost incomprehensibly large number, but it is still finite. It is still a limit, and it translates directly into a maximum feeding rate. If a black hole is shining at its Eddington luminosity, you can work backward to figure out how much mass it must be consuming to produce that much light. The conversion is not perfect. Not all of the infalling mass gets turned into radiation. Some of it, usually around 10%, gets converted into light through friction and magnetic interactions in the accretion disk. The rest crosses the event horizon and adds to the black hole's mass. Run the numbers and you find that a black hole feeding at the Eddington limit can grow at a rate of roughly 1 solar mass per year for every 10 million solar masses it already weighs. A 1 million solar mass black hole maxes out at about 0.1 solar masses per year. A 1 billion solar mass black hole can eat up to 100 solar masses per year. A 100 billion solar mass black hole could theoretically consume 10,000 solar masses per year if it is feeding at the absolute maximum rate physics allows. That sounds like a lot. It is a lot, but here is the catch. Black holes do not start out weighing 100 billion solar masses. They start small. The first black holes in the universe formed from the collapse of massive stars. Those stellar remnants weighed somewhere between a few solar masses and maybe a few hundred solar masses at most. To grow from 100 solar masses to 100 billion solar masses, the black hole needs to gain mass by a factor of 1 billion. If it is feeding at the Eddington limit the entire time, which is already an optimistic assumption, the math says it takes roughly 50 million years for a black hole to double its mass. Start with 100 solar masses, wait 50 million years, now you have 200 solar masses. Wait another 50 million years, 400. Wait another 50 million, 800. You can see where this is going. Exponential growth is powerful, but it is not instantaneous. To grow by a factor of 1 billion, you need to double roughly 30 times. 30 doublings at 50 million years per doubling comes out to 1.5 billion years. That is the absolute minimum time required to grow a 100 billion solar mass black hole from a stellar remnant if it feeds continuously at the Eddington limit with perfect efficiency and never stops. Now factor in reality. Black holes do not feed continuously. Gas does not fall in at a steady rate. Accretion disks are turbulent, chaotic, and prone to instabilities. The black hole's environment changes. Galaxies merge, gas clouds get disrupted, star formation consumes available material. There are long periods where the black hole is essentially starving, pulling in almost nothing. During those times, it does not grow. The clock stops. When you average out the feeding rate over billions of years, most supermassive black holes are thought to spend the majority of their lives well below the Eddington limit. Some estimates put the average accretion rate at closer to 1% or even 0.1% of the Eddington rate. If that is true, the growth timescale stretches from 1.5 billion years to 15 billion years or longer. And that is a problem because the universe is only 13.8 billion years old. Phoenix A star weighs 100 billion solar masses. We are seeing it as it existed 5.7 billion years ago, which means it had already reached that mass by the time the universe was roughly 8 billion years old. 8 billion years to grow from a stellar mass black hole to 100 billion solar masses through steady accretion is not just difficult, it is borderline impossible. The numbers do not fit. Even if the black hole fed at the Eddington limit every single day for 8 billion years without pausing, it would barely make it. And we know that is not what happens. So either Phoenix A star started out much heavier than a stellar remnant, or it grew faster than the Eddington limit allows, or it gained most of its mass through a process that does not involve steady accretion. All three possibilities require us to rethink how supermassive black holes form. The standard model of black hole growth has two main pathways. The first is accretion. Gas falls in, the black hole gets heavier, repeat for billions of years. This is the slow burn. It is how most black holes are thought to grow during the quiet periods of cosmic history. The second pathway is mergers. Two galaxies collide. Their central black holes eventually sink to the center of the merged system, and after losing enough orbital energy, they spiral together and merge into a single larger black hole. Mergers are faster than accretion in the sense that they can add huge amounts of mass in a relatively short time. If two black holes, each weighing 10 billion solar masses, merge, you instantly get a 20 billion solar mass black hole. No waiting, no slow feeding. Just a violent collision that releases more energy and gravitational waves than all the stars in the observable universe emit in light over the same period. But mergers are also rare. Galaxies do not collide every day. And even when they do, it can take hundreds of millions of years for the black holes to actually meet. Here is where the story gets interesting. Rare does not mean impossible. And in the early universe, rare events were happening a lot more often than they do today. The universe was smaller. Galaxies were closer together. Dark matter halos, the invisible scaffolding that holds galaxies together, were denser and more likely to overlap. In that environment, galaxy collisions were common, not occasional, common. Some regions of space were so crowded with proto-galaxies that mergers were happening continuously, one after another, in a kind of cosmic demolition derby. And every time two galaxies merged, their black holes merged too. Or at least they were supposed to. The process is not guaranteed. If the galaxies collide at the wrong angle or with too much speed, the black holes can get ejected from the system entirely, flung out into intergalactic space as rogue objects. But when the geometry is right, when the collision is slow and head-on, the black holes settle into the center of the merged galaxy and begin the long process of spiraling toward each other. That process is driven by a mechanism called dynamical friction. As a black hole moves through a sea of stars and dark matter, it gravitationally tugs on everything around it. Those tugs slow the black hole down, sapping its orbital energy and causing it to sink toward the center of the galaxy. It is a bit like moving through a crowd. Every person you bump into slows you down slightly. The black hole experiences the same effect, but instead of people, it is interacting with billions of stars and trillions of dark matter particles. Over time, the black hole loses enough energy that its orbit shrinks. If there are two black holes in the same galaxy, they both sink toward the center, and eventually they find each other. Once they are close enough, within a few light years or so, they start emitting gravitational waves. Those waves carry energy away from the system, and the black holes spiral inward faster and faster until they collide. The final merger is violent but brief. In the last fraction of a second before the event horizons touch, the black holes are orbiting each other hundreds of times per second. The gravitational waves they emit are so strong that they warp spacetime itself into ripples that propagate outward at the speed of light. When the event horizons finally merge, the two black holes become one. The new black hole is heavier than the sum of its parts because some of the original mass has been radiated away as gravitational wave energy, but the amount lost is small, usually a few % at most. The rest becomes part of the new black hole. And if that new black hole is sitting in a galaxy that is still actively merging with other galaxies, the process can repeat. Another collision, another black hole sinking inward, another merger, over and over. This is the merger hypothesis for how supermassive black holes grow beyond the Eddington limit. It is not that the limit stops applying, it is that mergers bypass the limit entirely. During a merger, no gas is falling in, no accretion disk is radiating, no photons are pushing back. The mass transfer happens gravitationally through the collision itself, and gravity does not have a speed limit the way accretion does. You can add billions of solar masses to a black hole in the time it takes the two objects to spiral together and merge, which, depending on how close they start, can be anywhere from a few million years to a few tens of millions of years. That is fast. Faster than accretion by orders of magnitude. Now imagine this happening not once but dozens of times. Phoenix A star sits in the Phoenix cluster, one of the most massive galaxy clusters in the observable universe. That cluster is not a quiet place. It is a gravitational battleground where galaxies have been colliding and merging for billions of years. The central galaxy, the one that hosts Phoenix A star, is what astronomers call a brightest cluster galaxy, or BCG. These are the monsters of the galaxy world, sitting at the bottom of the cluster's gravitational well and growing by cannibalizing everything around them. Every time a smaller galaxy falls into the cluster and gets too close to the BCG, it is torn apart by tidal forces. Its stars get stripped away and absorbed into the BCG's halo. And its central black hole, if it has one, sinks toward the center and merges with the black hole already there. If the Phoenix cluster has been doing this for most of its history, Phoenix A star could have grown through dozens or even hundreds of mergers. Start with a seed black hole weighing a few million solar masses. Let it merge with another black hole of similar size. Now you have 10 million solar masses. Merge again, 20 million, merge again, 40 million. The growth is exponential, just like accretion, but the time scale is much shorter. Each merger takes tens of millions of years instead of hundreds of millions. Over the course of 8 billion years, you can fit in a lot of mergers, enough to reach 100 billion solar masses without ever violating the Eddington limit, because you are not relying on accretion. You are relying on collisions. The role of dark matter in this process cannot be overstated. Dark matter makes up roughly 85% of the matter in the universe, and it is the reason galaxies and galaxy clusters hold together at all. Without dark matter, the visible matter, the stars and gas, would not have enough gravitational pull to stay bound. Galaxies would fly apart. Clusters would never form. But dark matter does more than just hold things together. It also acts as a gravitational glue that pulls galaxies toward each other. In the early universe, when dark matter halos were denser and more concentrated, that pull was even stronger. Galaxies sitting inside overlapping dark matter halos were almost guaranteed to collide, and once they collided, the dark matter helped drag the black holes toward the center of the merged system, speeding up the process of dynamical friction. Some researchers have suggested that the early universe was uniquely suited for building supermassive black holes precisely because of this. The combination of dense dark matter halos, abundant gas, and frequent galaxy collisions created an environment where black holes could grow extremely fast, not through steady feeding, but through rapid-fire mergers punctuated by occasional bursts of super Eddington accretion during the chaotic moments right after a collision when gas was being funneled toward the center of the merged galaxy. In that scenario, Phoenix A star is not an outlier. It is the natural result of living in one of the universe's most violent neighborhoods for billions of years. There is another possibility, one that is even more speculative but gaining traction among theorists. What if Phoenix A star did not start out as a stellar mass black hole at all? What if it started out already weighing millions or even tens of millions of solar masses? These are called seed black holes, and they come in two flavors. The first is intermediate mass black holes, objects that form in dense star clusters through runaway collisions where stars smash into each other faster than they can disperse. This process can build black holes weighing thousands of solar masses in just a few million years. If one of these intermediate mass black holes ends up at the center of a young galaxy, it has a massive head start. Instead of needing to grow by a factor of 1 billion, it only needs to grow by a factor of 10,000 or so. That is still exponential growth, but the timescale is much more manageable. The second flavor is even more extreme. Direct collapse black holes. These are objects that form when enormous clouds of primordial gas, untouched by previous generations of stars, collapse all at once without fragmenting. Under normal circumstances, gas clouds break apart as they collapse. Denser regions pull away from less dense regions, and each clump becomes a star. But if the gas is hot enough, if it is rotating slowly enough, and if there is no dust or heavy elements to cool it down, the entire cloud can stay intact. It collapses as a single unit, and the result is a black hole that starts out weighing hundreds of thousands or even millions of solar masses. No stars, no supernovae, just a black hole, born fully formed in the first few 100 million years after the Big Bang. If Phoenix, a star formed from a direct collapse seed, it could have started life already weighing 10 million solar masses or more. From there, 8 billion years of mergers and occasional feeding would be more than enough to reach 100 billion. We do not know which of these scenarios is correct. We might never know. The events that built Phoenix a star happened billions of years ago in a part of the universe we can only see as it was, not as it is now. The black hole itself offers no clues about its past. Black holes have no memory, no internal structure, no record of what fell in or when. The only things that define a black hole are its mass, its spin, and its electric charge. Everything else is erased. But we can make educated guesses based on what we see around it. The Phoenix cluster is massive. It is active. It has a cooling flow that is pouring hundreds of solar masses of gas toward the center every year. That tells us the environment has been rich with material for a long time. The central galaxy is enormous, one of the largest galaxies in the universe. That tells us it has been cannibalizing its neighbors for billions of years, and Phoenix A star itself is feeding at a rate of 60 solar masses per year, which is well below its Eddington limit, but still fast enough to suggest that gas is available and falling in. All of that points toward a history of violence. Mergers, collisions, gas inflows, and a black hole that has been growing steadily, if not continuously, for most of the universe's history. The Eddington limit is not a wall, it is a throttle, and under the right conditions, that throttle can be bypassed entirely. Mergers do not care about radiation pressure. They add mass gravitationally, instantly, without triggering the feedback mechanisms that shut down accretion. If Phoenix, a star, grew primarily through mergers, the Eddington limit was never the obstacle. The obstacle was whether enough galaxies collided in the right place at the right time to build something this massive, and in the Phoenix cluster, the answer appears to be yes. The cluster provided the collisions, the dark matter halos provided the gravity to pull the black holes together, and time did the rest. 8 billion years is a long time. Long enough for dozens of major mergers, long enough for a black hole to grow from a seed, whatever that seed was, into the largest confirmed black hole in the universe. But here is the part that keeps astronomers up at night. Phoenix A star is still growing. It has not stopped. It is not a relic from the early universe, sitting quietly in the dark. It is active. It is feeding. And the environment around it, the cooling flow, the star formation, the gas inflows, all of it suggests that the cluster still has fuel, which means Phoenix A star could get bigger. Not by a little, by a lot. If the current feeding rate is sustained, the black hole will gain another billion solar masses in less than 17 million years. That is a rounding error in cosmic time. And if the mergers continue, if the cluster keeps cannibalizing smaller galaxies and funneling their black holes toward the center, Phoenix A star could double in size in the next few billion years. 100 billion solar masses is not the end. It is just where we happen to catch it. The implications of that are staggering. If black holes can grow beyond 100 billion solar masses, then the models that predict a natural cutoff are wrong. And if the models are wrong about the upper limit, they might be wrong about other things too. How common are objects like Phoenix A star? How many of them are out there that we have not found yet? And what happens to a galaxy when its central black hole weighs more than half the total mass of all its stars? Does the galaxy become a satellite of the black hole instead of the other way around? Does the black hole eventually consume the entire galaxy, leaving nothing behind but a naked singularity surrounded by darkness? These are not rhetorical questions. They are the kinds of questions that open up entire new fields of research, and Phoenix A star is the key to answering them. The star formation rate in the Phoenix cluster is not slowing down. If anything, it is accelerating. 800 solar masses per year is one of the highest rates ever measured, and it shows no sign of stopping. That gas has to go somewhere. Some of it is forming stars. But some of it, maybe a lot of it, is falling toward the center, toward Phoenix A star. The black hole is eating, and the buffet is still open. The black hole is still eating, and the buffet is still open. That much we have established. Phoenix A star sits at the center of its cluster, weighing somewhere in the neighborhood of 100 billion solar masses, feeding at a rate of 60 suns per year, and growing steadily despite every rule in the book saying it should have stopped billions of years ago. That is the first paradox. The second paradox is worse. Because while Phoenix A star has been busy breaking the laws of black hole growth, it has also been failing spectacularly at the one job every supermassive black hole is supposed to do: kill stars before they are born. Let me be clear about what that means. Supermassive black holes are not passive objects sitting quietly at the centers of galaxies. They are regulators, thermostats, cosmic executioners whose sole function, at least according to the last 2 decades of astrophysical consensus, is to prevent their host galaxies from turning into runaway star factories. They do this through a process called active galactic nucleus feedback, or AGN feedback for short. The mechanism is straightforward. When a black hole feeds, it does not just get heavier, it gets loud. Matter spiraling inward through the accretion disk heats up to millions of degrees. That heat produces radiation. X-rays, ultraviolet light, sometimes gamma rays. The radiation slams into nearby gas, heating it even further, driving it outward. At the same time, the black hole launches jets, narrow beams of plasma accelerated to nearly the speed of light by magnetic fields twisted around the black hole's spin. Those jets punch through the surrounding gas like a blowtorch through fog, carving cavities light years across and pumping enormous amounts of energy into the environment. The result is that the gas around the black hole gets too hot to collapse. Stars form when cold gas clouds lose enough energy that gravity takes over and pulls them inward. The gas condenses, fragments into smaller clumps, and each clump collapses into a star. But if the gas is heated to tens of millions of degrees by AGN feedback, it does not condense, it does not fragment, it just sits there too energetic to collapse, glowing in X-rays while the black hole quietly chokes off any chance of new stars forming. This is not speculation. This is observed behavior in galaxy cluster after galaxy cluster. Astronomers have watched it happen. They have mapped the cavities blown by black hole jets. They have measured the gas temperatures. They have counted the stars, or more accurately, counted the lack of stars. And the pattern is consistent. Big black hole equals hot gas equals no star formation. That is the rule. That is how the universe self-regulates. Without AGN feedback, every massive galaxy would exhaust its gas supply in a few 100 million years, bloating into a monster packed with so many stars that it would outshine entire clusters. With AGN feedback, galaxies stay lean. The black hole acts as a brake, keeping star formation in check, ensuring the system stays in balance for billions of years. The Phoenix cluster does not care about balance. It is forming stars at a rate of roughly 1,000 solar masses per year. Not a handful, not a trickle. 1,000, that is not a typo. 1,000 times the mass of our Sun turned into new stars every single year. To put that in perspective, the Milky Way forms about 2 solar masses worth of stars per year, maybe 3 in a good year. The Phoenix cluster is outpacing our galaxy by a factor of more than 300. It is one of the highest star formation rates ever measured in a galaxy cluster, and it is happening in an environment that should be completely sterile. Star formation at this scale requires 2 things: cold gas and lots of it. The gas has to be cold enough that gravity can pull it together without thermal pressure blowing it apart. In most galaxy clusters, the gas is far too hot, tens of millions of degrees, sometimes hotter. At those temperatures, the gas is moving so fast that gravity cannot hold it down. It disperses, it floats, it does everything except collapse into stars. The Phoenix cluster has cold gas, lots of it. Observations from the Atacama Large Millimeter Array ALMA have detected massive reservoirs of molecular hydrogen sitting in the core of the cluster. Molecular hydrogen is the coldest, densest form of gas in the universe. It is the raw material from which stars are made, and there is enough of it in the Phoenix cluster to keep churning out stars at the current rate for tens of millions of years. That gas is not sitting at the edges of the cluster where it might be shielded from the black hole's influence. It is sitting right in the core, right where Phoenix A star should be heating it, blowing it away, shutting it down, and it is not being shut down. It is condensing, collapsing, forming stars. This is the cooling flow problem, and it has been one of the most persistent puzzles in astrophysics for more than 40 years. The problem was first identified in the 1980s when astronomers started noticing that galaxy clusters were surrounded by enormous halos of hot X-ray emitting gas. That gas, heated by the gravitational collapse of the cluster itself, should be radiating energy away as X-rays. When gas radiates, it loses energy. When it loses energy, it cools. When it cools, it loses pressure. And when it loses pressure, gravity takes over. The gas should fall inward toward the center of the cluster, piling up around the central galaxy, cooling further as it compresses, and eventually condensing into stars. Lots of stars, hundreds or thousands of solar masses per year. The math was clean. The predictions were solid. Astronomers called these systems cooling flows and expected them to be the dominant mode of star formation in massive galaxy clusters. Then they looked and found almost nothing. Most clusters were forming stars at a fraction of the predicted rate, a few solar masses per year at most, sometimes none at all. The cooling flows were not flowing. Or more accurately, the gas was cooling and falling inward, but it was not making it all the way to the center. Something was stopping it. Something was heating the gas back up before it could collapse. The culprit, it turned out, was the central black hole. AGN feedback. The black hole was eating just enough gas to keep its jets running, and those jets were pumping energy back into the cluster, reheating the gas, preventing it from cooling all the way down. Problem solved. Cooling flows were dead. Star formation was quenched. The universe was back in balance. Except the Phoenix cluster missed the memo. The cooling flow is running. The gas is falling. The stars are forming. And Phoenix, a star, the thing that is supposed to be stopping all of this, is just sitting there, feeding, growing, and completely failing to regulate anything. Prithvi Nataraja, a theoretical astrophysicist at Yale and one of the leading researchers studying the formation of supermassive black holes, has spent years puzzling over this exact problem. In interviews following the discovery of the Phoenix cluster's extreme star formation rate, she noted that jets from black holes this massive are supposed to prevent star formation by heating the gas. Quenching is what is supposed to happen, but here the opposite is happening. The black hole is active. The jets are firing. The X-ray emission from the cluster is off the charts, 7 times brighter than a typical massive cluster. All of that points to a black hole that is dumping enormous amounts of energy into its environment, and yet the gas is still condensing. The stars are still forming. Something is broken. Either the feedback mechanism is not working the way it should, or the cluster has so much gas pouring inward that even a 100 billion solar mass black hole cannot keep up. Let me give you a sense of how much gas we are talking about. The Phoenix cluster contains roughly 10 trillion solar masses of hot gas. That is the total mass of the X-ray emitting halo surrounding the galaxies. Not all of that gas is available for star formation. Most of it is too hot, too diffuse, too far from the center. But even a small fraction of 10 trillion is an enormous number. If just 1% of that gas cools and falls inward over the next few 100 million years, you are looking at 100 billion solar masses of raw material, enough to form a galaxy the size of the Milky Way from scratch. And the gas is not cooling slowly. It is cooling fast. Fast enough that by the time it reaches the core of the cluster, it has dropped from tens of millions of degrees down to a few hundred degrees, cold enough for molecules to form, cold enough for gravity to win, cold enough to make stars. The current hypothesis, and it is very much a hypothesis, is that the cooling flow in the Phoenix cluster is so strong that the black hole simply cannot stop it. Phoenix A star is feeding at 60 solar masses per year. That is fast by most standards. But the cooling flow is delivering gas to the center at a rate of more than 1,000 solar masses per year. The black hole is eating 6% of what is falling in. The rest is bypassing it entirely, flowing around the accretion disk, condensing into clouds, and collapsing into stars before the black hole's jets can heat it back up. In that scenario, Phoenix A star is not failing to do its job. It is being overwhelmed. The cluster is pouring so much gas inward that even a black hole this massive, feeding at a rate well above what most black holes ever achieve, is not powerful enough to shut down the inflow. The black hole is trying. It is just losing. There is another possibility, one that is even more unsettling. What if the black hole is not trying to stop the star formation? What if it is causing it? This is not as crazy as it sounds. AGN feedback is usually described as a negative feedback loop. The black hole heats the gas stops collapsing, the star formation shuts down. But there is another kind of feedback, positive feedback, where the energy from the black hole does not disperse the gas but compresses it. Think of it like a shock wave from an explosion. If you are too close, the blast tears you apart. But if you are at just the right distance, the shock wave can push material together, compressing it into denser clumps that are more likely to collapse under their own gravity. The same thing can happen with black hole jets. If the jets are powerful enough and aimed at dense clouds of gas, they can compress those clouds, triggering star formation instead of preventing it. There is some observational evidence for this in other systems. Astronomers have found star-forming regions sitting at the edges of jet-blown cavities in other galaxy clusters, young stars a few million years old, sitting exactly where the jet appears to have compressed the surrounding gas. The process is called jet-induced star formation, and it is one of the ways AGN feedback can have unintended consequences. The black hole is trying to heat the gas and blow it away, but in doing so, it creates dense shells of material that collapse into stars. In most cases, this effect is minor. A few extra stars here and there, nothing that changes the overall picture. But in the Phoenix cluster, where the gas is already unusually dense and the cooling flow is already unusually strong, jet-induced star formation might not be a minor effect. It might be the dominant effect. The black hole might be inadvertently seeding the very star formation it is supposed to suppress. This is the failed executioner narrative. Phoenix, a star, the largest black hole in the known universe, is supposed to be the ultimate regulator, the final word in cosmic population control, and instead it is presiding over one of the most vigorous episodes of star formation ever observed. It is a wildfire that creates forests, a demolition crew that builds skyscrapers, a thermostat that heats the house by trying to cool it. The analogy breaks down because the black hole is not trying to do anything. It is just a region of curved spacetime that happens to be very good at eating matter and very bad, in this specific case, at stopping star formation. But the result is the same. The Phoenix cluster is thriving. Its central galaxy is glowing with the light of billions of young stars. And the black hole at its heart, the thing that should have sterilized the environment billions of years ago, is sitting there, growing, feeding, and watching it all happen. Now here is where it gets even stranger. The star formation in the Phoenix cluster is not evenly distributed. It is concentrated in the core. Within a few 100,000 light-years of Phoenix A star, the gas is cold, dense, and collapsing into stars at a furious rate. Beyond that radius, the star formation drops off sharply. The outer regions of the cluster are behaving normally. The gas is hot, the stars are old, everything is quiet. It is only the core that is going haywire. That tells us something important. The cooling flow is not a cluster-wide phenomenon. It is localized. Something about the core environment is different. Something is allowing the gas to cool and collapse in a way that does not happen anywhere else in the cluster, and the most obvious candidate is the black hole itself. Not because it is shutting down star formation, because it is enabling it. One hypothesis that has gained traction is that the jets from Phoenix A star are not constant. They are episodic. They fire for a few million years, heating the gas, blowing cavities, doing all the things jets are supposed to do. Then they shut off. The black hole stops feeding, or feeds more quietly, and the jets disappear. Without the jets, the gas is free to cool. It falls inward, condenses, forms stars. Then the black hole wakes up again. The jets fire. The cycle repeats. This kind of episodic feedback has been observed in other systems. It is one of the ways AGN feedback can be less efficient than the simple models predict. The black hole is not a steady regulator. It is a flickering one. And during the off periods, the star formation sneaks through. If that is what is happening in the Phoenix cluster, the current burst of star formation might not last. The black hole might be in the middle of a quiet phase, and in a few million years, the jets could fire up again and shut everything down. Or the jets might already be firing, and the star formation we are seeing now is the tail end of a cooling flow that has been running for tens of millions of years and is about to be quenched. We do not know. We are seeing the cluster as it was 5.7 billion years ago. By now, in the cluster's present, the situation could be completely different. The stars we are detecting might be ancient by their own local clock. The cooling flow might have stopped. Phoenix A star might have finally caught up and shut it all down. Or it might still be running, still forming stars, still defying the models. We will not know for another 5.7 billion years when the light from the cluster's present finally reaches us. And by then, we will have other problems. There is one more piece of the puzzle that does not fit. The gas in the Phoenix cluster is cold, but it is not primordial. It is enriched. Astronomers can tell by looking at the spectrum of the X-ray emission. The gas contains heavy elements, oxygen, carbon, nitrogen, iron, elements that can only be produced inside stars. That means the gas falling toward the center of the cluster is not leftover material from the Big Bang. It is recycled. It is the guts of stars that lived and died and exploded, seeding the cluster with the building blocks of planets and life and everything that comes after. That enriched gas is now collapsing into new stars. Those stars will eventually die, explode, and enrich the gas even further. The cycle repeats. The cluster is not just forming stars, it is recycling them, over and over, building new generations from the ashes of the old. This is rare. Most galaxy clusters stopped forming stars billions of years ago. They exhausted their cold gas, or their central black holes shut down the cooling flows, and the star formation ground to a halt. The galaxies in those clusters are red and dead, old stars, no new ones. The Phoenix cluster is young by comparison, vibrant, alive. Its central galaxy is blue with the light of massive young stars, stars that are only a few million years old, sometimes less. That blue light is the signature of ongoing star formation. It is the cosmic equivalent of a heartbeat. And the fact that it is happening at all, in a cluster this massive, around a black hole this large, means something fundamental about our understanding of AGN feedback is incomplete. Natarajan has suggested that the key might be the efficiency of cooling. In most clusters, the gas cools slowly. It radiates X-rays, loses energy, but the cooling timescale is longer than the heating timescale from AGN feedback. The black hole can keep up. It heats the gas just fast enough to balance the cooling, and the system stays in equilibrium. No star formation. But in the Phoenix cluster, the gas might be cooling so efficiently that the black hole cannot keep up. The cooling timescale is shorter than the heating timescale. The gas loses energy faster than the jets can pump it back in. The equilibrium breaks, the gas collapses, stars form. If that is true, the Phoenix cluster is not an outlier. It is an example of what happens when the cooling wins. And if there are other clusters out there where the cooling is efficient enough to overwhelm AGN feedback, we should find more systems like this. So far we have not. The Phoenix cluster appears to be unique, which either means it is extraordinarily rare or we have not been looking hard enough. The 1,000 stars per year number is not a guess. It is derived from observations of the infrared and ultraviolet light coming from the core of the cluster. Young massive stars emit most of their light in the ultraviolet. That light gets absorbed by dust, which re-radiates it in the infrared. By measuring both wavelengths and accounting for the dust, astronomers can estimate how many stars are forming and how fast. The answer for the Phoenix cluster is roughly 740 to 1,000 solar masses per year, depending on which study you read and which assumptions you make about the initial mass function, the distribution of star masses. Either way, it is enormous. It is more star formation than happens in most entire galaxies, and it is happening in the core of a single cluster, in a region a few 100,000 light-years across. That region is also one of the most hostile environments in the universe. The gas is hot, the radiation is intense, the gravitational field is so strong that it warps space-time measurably. Anything trying to form a star in that environment has to overcome not just the usual obstacles, gravity versus pressure, but also the constant bombardment of X-rays from the cluster gas and the jets from the black hole. The fact that stars are forming at all is remarkable. The fact that they are forming at this rate is absurd. And the fact that the black hole, the thing that should be making it impossible, is instead sitting there feeding and growing while the stars pop into existence around it, suggests that the relationship between black holes and their host galaxies is more complicated than anyone thought. The failed executioner narrative is not just a metaphor, it is a testable hypothesis. If Phoenix A star is failing to quench star formation because the cooling flow is too strong, then we should see similar behavior in other clusters with similarly strong cooling flows. If Phoenix A star is actually triggering star formation through jet compression, we should see young stars sitting at the edges of the jet-blown cavities. If the feedback is episodic, we should see evidence of past outbursts, older cavities and shocks in the gas that line up with earlier episodes of jet activity. All of these predictions can be tested with better observations, deeper X-ray images, higher resolution infrared maps, spectroscopy of the gas to measure its velocity and temperature in detail. The data is coming. The James Webb Space Telescope has already started observing the Phoenix cluster. The Atacama Large Millimeter Array is mapping the cold gas, and within the next decade, next-generation X-ray telescopes will be able to resolve the structure of the hot gas around Phoenix A star in enough detail to see exactly where the cooling is happening and where the heating is failing. Until then, we are left with the paradox. A black hole that weighs 100 billion solar masses feeds at 60 solar masses per year and presides over a cluster forming 1,000 stars per year. A system that should be dead is alive. A regulator that should be shutting everything down is watching it thrive. And the largest black hole in the universe is sitting at the center of it all, growing, feeding, and doing absolutely nothing to stop it. The universe, it turns out, is not as self-regulating as we thought. Or maybe it is. Maybe Phoenix A star is regulating, just not in the direction we expected. Maybe the black hole is not a brake. Maybe it is an accelerator, a seed, a trigger, something that does not kill galaxies but births them. And if that is true, if black holes this massive can enable star formation instead of suppressing it, then everything we thought we knew about how galaxies grow, how they age, how they die, needs to be rewritten. The core of the Phoenix cluster is glowing, 1,000 stars per year, each one a sun, each one a potential system of planets, moons, asteroids, comets, each one a tiny furnace where hydrogen fuses into helium, and the universe builds the elements that will one day become rocks, oceans, atmospheres, life, all of it happening in the shadow of the largest black hole we have ever found, a black hole that should have made none of it possible. And yet here we are. The stars are shining, the gas is collapsing, the black hole is watching. And somewhere in the core of that cluster, in a region of space so dense and so bright that it outshines galaxies, the universe is doing something it is not supposed to do. It is building a cradle right next to a grave. And the boundary between the two is so thin that no one can tell where one ends and the other begins. The core of the Phoenix cluster is glowing, 1,000 stars per year, each one a sun, each one a potential system of planets, moons, asteroids, comets, each one a tiny furnace where hydrogen fuses into helium and the universe builds the elements that will one day become rocks, oceans, atmospheres, life. All of it happening in the shadow of the largest black hole we have ever found. A black hole that should have made none of it possible, and yet here we are. The stars are shining, the gas is collapsing, the black hole is watching, and somewhere in the core of that cluster, in a region of space so dense and so bright that it outshines galaxies, the universe is doing something it is not supposed to do. It is building a cradle right next to a grave, and the boundary between the two is so thin that no one can tell where one ends and the other begins. Which brings us to the grave itself, the event horizon, the edge of Phoenix A star, the point of no return, and what it would actually feel like to cross it. Because that boundary, that razor-thin shell separating the universe you can leave from the universe you cannot, is not what most people imagine. It is not a wall, it is not a barrier, it is not a surface you can touch or a threshold you can see. It is a coordinate, a mathematical abstraction made real by geometry, and crossing it, contrary to every instinct your brain is screaming at you right now, would feel like absolutely nothing. Let me explain why that is so deeply, fundamentally unsettling. Most people, when they think about black holes, picture something violent, a maelstrom, a vortex of destruction that reaches out and tears you apart long before you get anywhere near the center. That image comes from a real process called spaghettification, and it is exactly as ridiculous as it sounds. The idea is simple. Gravity gets stronger the closer you get to a massive object. If you are falling feet first toward a black hole, your feet are closer to the center than your head. That means your feet experience stronger gravity than your head. The difference in gravitational pull between your feet and your head creates a stretching force. Your body gets pulled into a long, thin strand, like pasta being stretched by a machine. Spaghettification. Astronomers did not name it. Science communicators did. And it stuck because the image is so visceral, so easy to picture, that it became the default mental model for what happens when you get too close to a black hole. For small black holes, that model is correct. A stellar mass black hole, one that weighs a few times the mass of our Sun, has an event horizon only a few kilometers across. The tidal forces near that horizon are extreme. If you tried to cross it, you would be ripped apart long before you reached the edge. Your body would not survive. Your atoms might not survive. You would be stretched into a stream of subatomic particles and smeared across the event horizon in a process so violent that calling it death would be generous. It would be disintegration, annihilation, the complete and utter destruction of everything that made you you. But Phoenix, a star, is not a stellar mass black hole. It is not even close. Phoenix, a star, weighs 100 billion times the mass of our Sun. Its event horizon is not a few kilometers across. It is 590 billion kilometers across. That is 3,900 astronomical units. The distance light travels in 22 days. And here is the thing about tidal forces. They do not scale linearly with mass. They scale with the curvature of spacetime. The bigger the black hole, the gentler the curvature at the event horizon. For a black hole the size of Phoenix A star, the tidal forces at the event horizon are negligible, not small, negligible, as in you would not feel them at all. Think about it this way. Tidal forces are caused by the difference in gravitational pull between 2 points. If those 2 points are close together relative to the size of the gravitational field, the difference is large. If those 2 points are far apart relative to the size of the field, the difference is small. Your body is about 2 meters tall. The event horizon of Phoenix A star is 590 billion kilometers across. The ratio between those two numbers is so absurdly skewed that the difference in gravitational pull between your head and your feet at the event horizon is effectively zero. You could cross the event horizon of Phoenix A star standing upright, arms at your sides, breathing normally, and you would not feel a thing. No stretching, no tearing, no spaghettification. Just a smooth, uneventful passage across the most significant boundary in the universe. That is the first layer of wrongness. The thing that should kill you does not. The second layer is worse, because even though you are not being torn apart, you are still doomed, absolutely, irrevocably doomed, and you would not know it until it was far too late. The event horizon is not a physical object. It is a region of spacetime where the curvature becomes so steep that every possible future direction points inward. Outside the event horizon, you have options. You can fire your rockets. You can turn around. You can, in principle, escape. Inside the event horizon, those options vanish. Not because something is holding you back, because the geometry of spacetime itself has changed. The direction you call outward no longer exists as a path you can follow into the future. Every trajectory, every possible motion leads inward toward the singularity. The speed of light is still the speed of light. The laws of physics are still the laws of physics. But the shape of the universe has bent so severely that escape is not difficult. It is impossible, geometrically impossible. In the same way that you cannot travel backward in time, you cannot travel outward from inside the event horizon. The future is inward. That is the only future there is. Here is what that means in practice. Imagine you are piloting a spacecraft toward Phoenix A star. You are still far away, a few light years out, and you can see the stars around the black hole behaving strangely. Their light bends into arcs and rings as space-time warps in the black hole's vicinity. This is gravitational lensing, the same effect astronomers use to study distant galaxies. The black hole is acting like a lens, bending the light from stars behind it into distorted shapes. As you get closer, the lensing gets more extreme. The stars behind the black hole smear into a bright ring surrounding a dark circle. That circle is the shadow, the photon sphere, the region where light can orbit the black hole. Inside that shadow there is nothing, no light, no stars, just black. You keep flying. The shadow grows larger. At some point, it fills half your field of view. Then more than half. The stars ahead of you are compressed into a narrow band. The stars behind you are stretched into a thin arc that wraps around the edges of your vision. And still, you do not feel anything unusual. No pull, no tug, just the steady, predictable acceleration of freefall. Your instruments are working, your life support is functioning, the radio is transmitting signals back to wherever you came from. Everything is normal. You are coasting through space the same way you have been for the entire journey, and then you cross the event horizon, and nothing happens. This is the part that breaks people's brains. Crossing the event horizon is not an event in the sense that you experience it. There is no flash of light, no jolt, no sensation of passing through anything. Locally, in your immediate vicinity, space-time is smooth. The curvature is continuous. There is no discontinuity, no sharp edge. You cross the horizon the same way you would cross an invisible line drawn on a flat plane. You do not see the line, you do not feel the line. You just keep moving forward, and at some point you realize you are on the other side. Except you would not realize it, because the horizon is not marked. There is no sign, no boundary. Just a coordinate in space-time that, from your perspective, looks and feels like every other coordinate you have passed through. But something has changed. You just do not know it yet. The radio signals you have been transmitting back to your point of origin are still leaving your spacecraft at the speed of light. But they are not making it out. They are traveling through space-time, following the straightest possible paths, and those paths are curving inward. The photons are moving at the speed of light relative to the local space-time. But the local space-time is falling inward faster than light can climb out. This is not a violation of relativity. Nothing is moving faster than light through space. But space itself is falling into the black hole, and it is carrying everything with it. The photons are still moving. They are just not getting anywhere. They are like salmon swimming upstream in a river that is flowing faster than they can swim. They are giving it everything they have, and they are still being swept downstream. From your perspective inside, everything still looks fine. The stars ahead of you are still visible. The instruments are still working. You can still see the universe outside, but the universe outside can no longer see you. The last signal you transmitted before crossing the horizon is still climbing outward, redshifting as it fights against the pull of the black hole's gravity, stretching to longer and longer wavelengths. To an outside observer, that signal never quite makes it out. It slows, it redshifts, it fades, you fade. Time dilation stretches your last moment before the crossing into an eternity, and from the outside you appear to freeze at the horizon, your image growing dimmer and redder and quieter until it vanishes entirely. But you do not freeze, you keep falling, and the universe you left behind is gone. Now here is where it gets worse. You are inside, the event horizon is behind you, and you start to notice that things are not quite right. The stars ahead of you, the ones you could still see after crossing, begin to compress into a smaller and smaller region of your field of view. Not because they are moving, because the geometry of space-time around you is warping your view. Light from the outside universe is still reaching you, but it is being bent so severely by the black hole's gravity that it all appears to be coming from a single direction, directly ahead. The rest of your view, the sides, the back, all of it is dark. Not because there is nothing there, because the light from those directions has already been swallowed. The only light still reaching you is the light that was ahead of you when you crossed, and even that is starting to fail. You fire your rockets, full thrust, every ounce of fuel you have. You point the nose of your spacecraft directly away from the singularity, and you burn, and you keep falling inward. Not because the rockets are not working, they are. You can feel the thrust, you can see the exhaust. The spacecraft is accelerating in the direction you are pointing, but the direction you are pointing is not outward anymore. It cannot be. The space-time around you has tilted so completely that every direction you can point is in some sense inward. You are not fighting gravity. You are fighting geometry. And geometry always wins. Time, from your perspective, is still moving forward. Your watch ticks normally. You breathe normally. The seconds pass the way they always have. But time outside, the time in the universe you left behind, is racing ahead. This is time dilation in reverse. Outside the event horizon, clocks near the black hole run slower than clocks far away. Inside the event horizon, the effect is so extreme that if you could somehow look back at the universe outside, you would see it aging at an accelerating rate. Hours for you would be centuries out there. Days for you would be millennia. If you could survive long enough to watch, you would see the stars around the black hole born, live and die in fast forward. Galaxies would shift and merge, the universe would evolve, and you would still be falling, still inside, still trapped. But you cannot survive long enough to see any of that, because even though the tidal forces at the event horizon were negligible, they are not negligible everywhere. The closer you get to the singularity, the steeper the curvature of space-time becomes, and the steeper the curvature, the stronger the tidal forces. At some point, long before you reach the singularity itself, the difference in gravitational pull between your head and your feet becomes significant. Then it becomes severe, then it becomes lethal. Your body begins to stretch, gently at first, a slight pulling sensation, then more, then more. Your bones crack, your organs rupture, your cells are torn apart, and still you fall, because there is nowhere else to go. The tidal forces do not stop you, they just reshape you, stretching you longer and thinner, compressing you from the sides, turning you into a narrow stream of matter spiraling inward. Spaghettification, not at the event horizon, deep inside, where the curvature is so extreme that not even the molecular bonds holding your atoms together can withstand the strain. And then you reach the singularity. Or more accurately, the singularity reaches you, because the singularity is not a point in space, it is a point in time, your future, the moment in space-time where the curvature becomes infinite and the equations of general relativity break down completely. We do not know what happens there. We cannot know. The singularity is hidden behind the event horizon, shielded from the outside universe by a boundary that no information can cross. Everything that falls in is erased. Every atom, every photon, every bit of information about what you were and where you came from, all of it compressed into a region of space-time so dense that it has no size, no structure, no internal features, just mass and spin and charge. That is all a black hole remembers. 3 numbers. Everything else is gone. That is the event horizon of Phoenix A star, a boundary 590 billion kilometers across, where the universe stops being a place you can leave and becomes a place you cannot. And the most terrifying part is not the violence. It is not the tidal forces or the singularity or the fact that you would be ripped apart and erased from existence. The most terrifying part is the emptiness, the complete and utter absence of anything you can do about it. You can be as smart as you want. You can have the best spacecraft, the most powerful engines, the most advanced technology humanity has ever devised. None of it matters. Once you cross, you are done. Not because you are not trying hard enough, because the geometry of the universe has changed in a way that makes escape impossible. You cannot outrun space-time. You cannot outthink it. You cannot bargain with it. It is not a force. It is not an opponent. It is just the shape of reality. And inside the event horizon, that shape only goes one way. Here is the philosophical gut punch. The event horizon represents the absolute boundary of human knowledge, not a practical boundary, an absolute one, We can speculate about what happens inside, we can write equations, we can run simulations, but we can never check our work. Because any experiment we send across the event horizon can never send back results. Any probe we drop in disappears. Any signal it tries to transmit gets swallowed. The information is lost, not hidden, lost. Erased from the universe in a way that violates every other principle of physics we know. In quantum mechanics, information is supposed to be conserved. You can scramble it, transform it, encode it in different ways, but you cannot destroy it. Black holes appear to destroy it, and we do not know how to reconcile that with the rest of physics. Stephen Hawking spent decades wrestling with this problem. He called it the black hole information paradox, and it is one of the deepest unsolved puzzles in theoretical physics. Hawking radiation, the faint glow of particles that black holes emit due to quantum effects near the event horizon, suggests that black holes do eventually evaporate. Over timescales so long that they make the current age of the universe look like a blink, black holes lose mass, shrink, and eventually disappear. If that is true, if black holes are not permanent, then what happens to the information that fell in? Does it come back out encoded in the Hawking radiation? Does it get destroyed? Does it leak into another universe? We do not know. Hawking himself changed his mind on the answer at least twice. The paradox is still open, the information is still missing, and Phoenix A star, with its 100 billion solar masses of swallowed matter, contains more missing information than any other object we have ever found. That missing information is not abstract. It is stars, entire stars, thousands of them, maybe millions. Every star that has ever wandered too close to Phoenix A star and crossed the event horizon is gone. The light it emitted, the planets that orbited it, the history of its formation, the elements it forged in its core, all of it erased, and Phoenix A star remembers none of it. The black hole weighs 100 billion solar masses. That is the only thing it knows about itself. It has no memory of whether that mass came from hydrogen gas or neutron stars or entire galaxies. It has no record of when it formed or how it grew or what it consumed along the way. It is a blank slate, a gravitational footprint with no context, the ultimate amnesia. And yet we can infer some of that history by looking at what is around it. The Phoenix cluster is rich with gas and stars. The cooling flow is pouring matter inward. The star formation rate is extreme. All of that suggests that Phoenix A star has been in a feeding frenzy for a long time, billions of years. The black hole has been eating, growing, accumulating mass at a rate that most black holes never achieve, and it is still eating. 60 solar masses per year. That is not a relic growth rate. That is active feeding. Right now, as you are reading this, matter is crossing the event horizon of Phoenix A star. Gas that was floating in the cluster a few million years ago is spiraling inward, heating up, glowing in X-rays and then vanishing across the boundary. Every second the black hole gains mass. Every second more information is lost, and the universe keeps no record. If you could hover just outside the event horizon of Phoenix A star, which you cannot because the radiation environment would kill you instantly, you would see time itself behaving strangely. Clocks on your spacecraft would tick slower than clocks far from the black hole, not by a little, by a lot. An hour for you could be a year for someone watching from Earth. The closer you get to the horizon, the more extreme the effect becomes. Right at the horizon, the time dilation becomes infinite. From the perspective of the outside universe, time stops. You would appear to freeze, suspended forever at the edge, never quite crossing. But from your perspective, time keeps flowing. You keep falling. You cross the horizon in finite time. The paradox is resolved by realizing that the two perspectives are measuring time differently. There is no universal clock, no objective now, just different reference frames, each with its own version of when things happen. And once you cross, your reference frame is cut off from the outside. Your now is no longer part of their now. You have exited the universe in a very real sense. You are still there, still experiencing time, still falling inward, but from the outside you are gone, frozen at the horizon, fading, vanishing, a ghost. That is what the event horizon of Phoenix A star represents. A one-way door into a place that is still technically part of the universe, but no longer connected to it. A pocket of space-time that has been severed from the rest of reality. And the door is enormous. 590 billion kilometers wide, 3,900 times the distance from the Earth to the Sun. You could fit the entire solar system inside the event horizon and still have room left over. And once inside, everything that makes the solar system what it is, the Sun, the planets, the asteroid belt, the Kuiper belt, every comet, every grain of dust, all of it would be cut off from the rest of the universe, falling inward. Doomed, erased. The gentleness of the crossing makes it worse. If the event horizon tore you apart, if the passage was violent and immediate, there would be a kind of clarity to it. A moment where you knew this is it, this is the end. But the crossing is smooth, uneventful. You drift across a line you cannot see, and for a while everything seems fine. The danger is not immediate, it is inevitable. You have time to think, time to understand what has happened, time to realize that no matter what you do, no matter how hard you try, you are not getting out. That psychological horror, that slow dawning realization, is worse than any physical pain, because pain ends. This does not end. It just keeps going, inward, always inward, until the geometry itself tears you apart and the singularity erases you completely. And here is the final twist. We do not actually know what happens at the singularity. General relativity predicts that the curvature of spacetime becomes infinite, but that prediction is almost certainly wrong. Infinities in physics are usually a sign that the theory has broken down, that it is being pushed beyond the regime where it applies. General relativity is a classical theory. It does not include quantum mechanics. And at the singularity, where distances become so small and densities become so large, quantum effects should dominate. We need a theory of quantum gravity to describe what really happens there, and we do not have one. String theory makes attempts, loop quantum gravity makes attempts, but none of them are complete, and none of them have been tested. The singularity is not just a physical mystery, it is a theoretical one, a blank spot on the map, where the equations fail and we have no idea what replaces them. Phoenix A star contains one of those blank spots at its center, a region of space-time where the laws of physics as we know them do not apply, and the event horizon is the shield that keeps us from ever seeing what is really going on. The cosmic censorship hypothesis, proposed by Roger Penrose, suggests that the universe never allows a naked singularity to form. Every singularity is hidden behind an event horizon. Every tier in space-time is covered by a boundary that prevents information from leaking out. If that is true, the event horizon is not just a feature of black holes. It is a fundamental safety mechanism built into the fabric of reality. A way for the universe to hide its own failures, to sweep the singularities under the rug and keep the rest of space-time functioning normally. Phoenix A star is the largest rug in the universe, and underneath it there is a hole in reality 100 billion times the mass of our Sun. A place where time ends, space collapses, and everything we think we know about physics stops working. And the only thing protecting us from seeing that nightmare is a boundary we can never cross and return from, which brings us back to the question we started with. How did Phoenix A star get this big? How does a black hole grow to 100 billion solar masses in the time available? The event horizon is a clue, because everything that crosses it adds to the black hole's mass. Every star, every gas cloud, every photon, all of it feeds the black hole, and once it is inside, it can never leave. The event horizon is not just a boundary, it is a trap, a one-way accumulation mechanism that has been running for billions of years. And if Phoenix I star formed early, if it started out heavy, if it had access to a steady supply of gas and stars and merging black holes, it could have been feeding continuously since the universe was less than 1 billion years old. 8 billion years of feeding, 8 billion years of growth, 8 billion years of matter crossing the event horizon and vanishing into the dark. That is long enough, just barely, but only if the conditions were perfect, only if the black hole never stopped eating, only if the universe gave it everything it needed to grow into the monster we see today. The event horizon of Phoenix A star is the edge of a question we cannot answer from this side. It is the boundary between what we can know and what we can only guess, and every piece of matter that crosses it takes another fragment of the answer with it, locked away forever, beyond reach, beyond rescue, beyond any hope of recovery. The black hole is growing, the event horizon is expanding, and with every second that passes, more of the universe disappears across that boundary, more information is lost, more of the past is erased, and we are left standing on the outside, watching, measuring, speculating, but never truly knowing what lies beyond. The event horizon is not just the edge of a black hole, it is the edge of understanding itself. The event horizon of Phoenix A star is the edge of a question we cannot answer from this side. It is the boundary between what we can know and what we can only guess, and every piece of matter that crosses it takes another fragment of the answer with it, locked away forever, beyond reach, beyond rescue, beyond any hope of recovery. The black hole is growing. The event horizon is expanding, and with every second that passes, more of the universe disappears across that boundary, more information is lost, more of the past is erased, and we are left standing on the outside, watching, measuring, speculating, but never truly knowing what lies beyond. The event horizon is not just the edge of a black hole, it is the edge of understanding itself, which brings us to the most uncomfortable question of all. Not what Phoenix A star is, not how big it is, not what it does to the space around it. The question that keeps physicists awake is simpler and far more disturbing. Where did it come from? How does a black hole weighing 100 billion times the mass of our Sun come into existence in a universe that is only 13.8 billion years old? Because when you run the numbers, when you trace the growth backwards, when you account for every known mechanism by which black holes gain mass, you hit a wall. The timeline does not work, the mass does not add up, and the only explanations that remain are the ones that force us to admit that something happened in the early universe that we have never directly observed, may never observe, and barely understand. This is the seed problem, and it is not unique to Phoenix A star. It applies to every supermassive black hole we have ever found. But Phoenix A star makes it worse because Phoenix A star is so absurdly massive that the usual hand-waving does not cut it anymore. The gap between what the models predict and what we are actually seeing is too wide to ignore. So let us walk through the problem step by step, because this is where the story of Phoenix A star stops being about a single object and starts being about a whole in our understanding of how the universe works. Black holes grow in two ways, accretion and mergers. We have covered this. Accretion is slow. The black hole pulls in gas, the gas heats up, radiates, and some of it crosses the event horizon. The Eddington limit governs how fast this can happen. For a black hole feeding at the maximum rate, it takes about 50 million years to double its mass. Start with a black hole that forms from the collapse of a massive star. Call it 100 solar masses. That is generous. Most stellar mass black holes weigh between 5 and 50 solar masses. 100 is on the high end. But let us give the black hole every advantage. 100 solar masses, Eddington limited growth, continuous feeding for 13.8 billion years. You end up with a black hole weighing a few billion solar masses, not 100 billion, a few billion. The math is exponential, but the timescale is not long enough. You cannot get there from here. Mergers help a lot. If two black holes collide, you instantly get a heavier black hole. No waiting, no slow accretion, just a violent collision that adds the masses together. If Phoenix A star grew primarily through mergers, you could reach 100 billion solar masses much faster than through accretion alone. But mergers require collisions, and collisions require galaxies to run into each other. And galaxies, even in the crowded early universe, do not collide every day. Each merger takes tens or hundreds of millions of years to complete. You need the galaxies to collide. You need the black holes to sink to the center of the merged system. You need them to lose enough orbital energy to actually meet. And then you need the whole process to repeat, over and over, dozens of times, maybe hundreds. It is possible. But it is statistically unlikely. Which means if Phoenix A star formed this way, it is an extreme outlier. The product of a merger history so violent and so perfectly timed that it should be one of a kind, except we do not think it is one of a kind. We think there are more black holes out there in this mass range. We just have not found them yet. Which means the problem is not that Phoenix A star is a fluke. The problem is that the models are missing something fundamental, something that allows black holes to grow faster or start heavier or both. And that something is the seed, the starting point, the object that eventually becomes a supermassive black hole. Because if you start with a heavier seed, you do not need as much time to reach 100 billion solar masses. The growth is still exponential, but the exponent starts at a higher number, and that changes everything. The standard story goes like this. In the early universe, the first stars formed from clouds of primordial hydrogen and helium. These stars were massive, hundreds of times the mass of our Sun. They burned hot and fast, lived for only a few million years, and then exploded as supernovae. Some of them, the very largest, did not explode. They collapsed directly into black holes. Those black holes were the seeds, the first generation. Weighing somewhere between 10 and a few hundred solar masses. From there, they grew through accretion and mergers over billions of years, eventually becoming the supermassive black holes we see at the centers of galaxies today. This is the stellar remnant seed model. And for a long time, it was the only game in town. The problem is that it does not work for the earliest supermassive black holes. Astronomers have found quasars actively feeding supermassive black holes, sitting at redshifts above 6. That means we are seeing them as they existed when the universe was less than 1 billion years old. Some of these quasars contain black holes weighing 1 billion solar masses or more. 1 billion solar masses, less than 1 billion years after the Big Bang. Run the numbers on stellar remnant seeds and you cannot get there. Even if the black hole feeds at the Eddington limit continuously, even if it never stops, even if every condition is perfect, there is not enough time. The universe is too young. The black hole is too heavy. Something else must have happened. Enter the intermediate mass black hole. This is the idea that in the dense cores of the earliest star clusters, stars did not just collapse into black holes one at a time, they collided. In a sufficiently dense environment, where stars are packed so tightly that they are practically touching, collisions are not rare. They are inevitable. A star smashes into another star. The collision produces a heavier star. That heavier star is now more massive, which means it has a stronger gravitational pull, which means it is more likely to collide with yet another star. The process runs away. You get a runaway collision cascade where dozens or hundreds of stars merge into a single object over the course of just a few million years. That object, too heavy to support itself, collapses into a black hole. Not a stellar mass black hole, an intermediate mass black hole, weighing thousands of solar masses, maybe tens of thousands. That is a much better starting point. Grow from 10,000 solar masses to 100 billion solar masses, and the timeline becomes much more manageable. You still need billions of years, but at least it is possible. The intermediate mass seed hypothesis solves part of the problem, but it creates a new one. We have never definitively observed an intermediate mass black hole. There are candidates, objects that might be intermediate mass black holes based on their gravitational influence or the X-ray emission from their surroundings, but none of them have been confirmed beyond doubt. The problem is that intermediate mass black holes are hard to detect. They are too small to behave like supermassive black holes, which sit at the centers of galaxies and dominate the gravitational dynamics. And they are too large to behave like stellar mass black holes, which we can detect through gravitational waves when they merge. Intermediate mass black holes fall into an observational gap, a mass range where our current instruments struggle to find them. That does not mean they do not exist. It just means we have not proven they do. And in science, if you cannot prove it, you cannot build a theory on it, at least not a solid one. So we move to the third option, the one that sounds insane until you realize it might be the only explanation that works. Direct collapse black holes. This is the idea that under very specific conditions in the early universe, massive clouds of primordial gas collapsed directly into black holes without ever forming stars. No stellar evolution, no supernovae, no intermediate steps. Just a cloud of gas weighing hundreds of thousands or even millions of solar masses collapsing all at once and forming a black hole fully formed. A seed black hole that starts life already weighing more than most globular clusters. From there, 8 billion years of growth is more than enough to reach 100 billion solar masses. The timeline works. The mass works. The physics, at least on paper, works. The problem is that we have never seen it happen. Let me explain how direct collapse is supposed to work, because the conditions required are so specific that they border on absurd. Start with a cloud of primordial gas, pure hydrogen and helium, no heavy elements, no carbon, no oxygen, no metals of any kind. This is important because heavy elements act as coolants. When gas contains even trace amounts of carbon or oxygen, those atoms can radiate energy away very efficiently, cooling the gas and allowing it to fragment into smaller clumps. Each clump becomes a star. But if the gas is pure hydrogen and helium, it cannot cool as efficiently. It stays hot, and if it stays hot, it resists fragmentation. The entire cloud can collapse as a single unit. But staying hot is not enough. The cloud also has to avoid forming stars through other mechanisms. Normally, as a gas cloud collapses, it heats up from the compression. If it heats up enough, hydrogen fusion can ignite, and you get a star. To prevent that, the cloud needs to be irradiated by an external source of ultraviolet light. Not too much, or the gas gets blown away. not too little, or stars start forming. Just the right amount to keep the hydrogen ionized and prevent it from cooling below a critical threshold. This is called the Lyman-Werner flux, and it is named after the specific wavelengths of ultraviolet light that can dissociate molecular hydrogen without ionizing the gas completely. If the Lyman-Werner flux is in the sweet spot, the gas stays hot, stays intact, and collapses without fragmenting. Now add rotation. Most gas clouds rotate at least a little bit because they form from turbulent regions of the universe where everything is spinning. Rotation creates angular momentum, and angular momentum resists collapse. If the cloud is rotating too fast, centrifugal forces balance gravity and the collapse stalls. The gas spreads into a disk instead of collapsing into a point. To form a direct collapse black hole, the cloud has to be rotating slowly, slowly enough that angular momentum does not stop the collapse. This is rare. Most gas clouds rotate too fast. But in the early universe, in regions where the gas has not been stirred by previous generations of stars, slow rotation is possible, unlikely but possible. Put all of these conditions together, a massive gas cloud, pure hydrogen and helium, no metals, irradiated by the right amount of ultraviolet light, rotating slowly, collapsing as a single unit. If all of that happens, the cloud does not fragment, it does not form stars. It just keeps collapsing, getting denser and denser, until the core becomes so compressed that it crosses the threshold for black hole formation. The result is a black hole weighing hundreds of thousands of solar masses, maybe more, formed in a single event lasting only a few million years, no stars, no supernovae, just a black hole, born fully formed in the first few 100 million years after the Big Bang. This is a direct collapse black hole, and if they exist, they solve the seed problem completely. Phoenix, a star, could have started life as a direct collapse seed weighing 1 million solar masses or more. From there, 8 billion years of feeding and mergers is more than enough to reach 100 billion. The question is, do they exist? And the answer is, we do not know. We have never directly observed a direct collapse black hole. We have simulations showing that the process can happen under the right conditions. We have theoretical models predicting where and when these objects should form, but we do not have a confirmed detection. The James Webb Space Telescope is looking. One of its primary science goals is to find the earliest black holes in the universe and determine how they formed. If Webb can find a black hole sitting at a redshift above 10, weighing 1 million solar masses or more, that would be strong evidence for direct collapse, because there is no other way to build something that heavy that fast. But so far, nothing definitive. Webb has found some very early galaxies with surprisingly massive black holes, which is suggestive, but not conclusive. The data is still coming in. The jury is still out. Here is why direct collapse black holes are so hard to find. They are supposed to form in the very early universe, less than a few 100 million years after the Big Bang. At those distances, at those red shifts, everything is incredibly faint. The light has been traveling for more than 13 billion years. It has been stretched by the expansion of the universe into the infrared, and even with a telescope as powerful as Webb, detecting a single black hole in that era, in that wavelength range, is like looking for a specific grain of sand on a beach at night with a flashlight. Possible, but incredibly difficult. And even if you find a candidate, you have to prove that it is a direct collapse black hole, and not just a black hole that grew unusually fast through some other mechanism. That requires detailed spectroscopy, measurements of the gas around the black hole, evidence of the specific conditions the direct collapse requires. All of that is observationally expensive. It takes time, it takes multiple instruments, and it takes luck. There is another problem. Direct collapse black holes, if they exist, should be extremely rare. The conditions required are so specific that most regions of the early universe would not meet them. You need pristine gas. You need the right amount of ultraviolet radiation. You need slow rotation. All of that has to happen in the same place at the same time. Most gas clouds do not meet even one of those criteria, let alone all of them. So even if direct collapse black holes can form, they should be few and far between. Which means the odds of Webb pointing at exactly the right patch of sky and catching one in the act are not great. It is not impossible, but it is not guaranteed either. We might find one next year. We might not find one for decades. And until we do, the direct collapse hypothesis remains just that, a hypothesis. Well motivated, consistent with the data we have, but unproven. Now let us talk about the alternative, the one that sounds even crazier, but is starting to gain traction among theorists who are willing to think outside the box. Primordial black holes. These are black holes that did not form from stars or gas clouds. They formed directly from the extreme density fluctuations in the first fraction of a second after the Big Bang. In the earliest moments of the universe, space-time was a roiling foam of quantum fluctuations. In some regions, the density was slightly higher. In others, slightly lower. Most of those fluctuations smoothed out as the universe expanded. But in rare cases, a density fluctuation was so extreme that it collapsed into a black hole before the universe could smooth it out. These are primordial black holes. They could have formed with any mass, from microscopic to millions of solar masses, depending on the size of the fluctuation. And if they formed in the first moments after the Big Bang, they have been around ever since. Sitting in the universe, growing, merging, potentially becoming the seeds of the supermassive black holes we see today. The appeal of primordial black holes is that they bypass all the problems with stellar remnants and direct collapse. They do not require stars. They do not require specific gas conditions. They just require the Big Bang to have been slightly lumpier than average in certain regions. If primordial black holes exist, they could have started life weighing millions of solar masses or more, giving them an enormous head start. From there, the growth to 100 billion solar masses is straightforward. Feed for a few billion years, merge with a few other black holes, and you are done. Phoenix A star could be a primordial black hole that has been growing since the universe was less than a second old. That is a seductive idea. It explains the mass, it explains the timeline, and it does not require any exotic physics beyond what we already know happened in the early universe. The problem is that primordial black holes are even harder to detect than direct collapse black holes. Because they formed so early, they have had billions of years to merge with other objects, accrete gas, and erase any evidence of their primordial origin. By the time we observe them, they look like any other supermassive black hole. There is no smoking gun, no unique signature that tells us this black hole formed in the first second after the Big Bang versus forming from a direct collapse event a few 100 million years later. The two scenarios produce the same end result, a very massive black hole sitting in the early universe. Distinguishing between them requires information we do not have and might never have. There is one possible way to test the primordial black hole hypothesis. If primordial black holes are common, they should contribute to the overall mass density of the universe. Specifically, they should contribute to dark matter. Dark matter is the invisible stuff that makes up 85% of the matter in the universe. We know it is there because we can see its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters are too massive. The cosmic microwave background has patterns that only make sense if there is a lot more matter than we can see. Dark matter explains all of that, but we do not know what dark matter is. The leading candidates are exotic particles that do not interact with light, but primordial black holes are another possibility. If enough primordial black holes formed in the early universe, they could account for some or all of the dark matter. The problem is that observations of the cosmic microwave background and the distribution of galaxies put tight constraints on how much of the dark matter can be in the form of black holes. The current limits suggest that primordial black holes, if they exist, make up only a small fraction of the dark matter. Not enough to be the whole story, but enough, potentially, to seed the first supermassive black holes. Here is where we stand. We have three main candidates for the seeds of supermassive black holes: stellar remnants, intermediate mass black holes, and direct collapse black holes. Primordial black holes are a fourth option, but they overlap significantly with direct collapse in terms of their observational signatures. Stellar remnants do not work for the earliest, most massive black holes. The timeline is too short. Intermediate mass black holes could work, but we have not found them. Direct collapse black holes could work, and the physics is sound, but we have not seen one form. Primordial black holes could work, but we have no direct evidence they exist in large numbers. That is the state of the field. 3.5 ideas, none of them proven, all of them plausible, and no clear way to decide between them based on the data we have right now. Phoenix A star does not care about our uncertainty. It exists. It weighs 100 billion solar masses. It formed somehow. And whatever mechanism built it, that mechanism has been confirmed by the universe itself. The black hole is real. The physics that made it possible is real. We just do not know what that physics is yet, and that is what makes Phoenix A star so important. It is not just a record breaker. It is a test case, a challenge thrown down by the universe saying, explain this. Build a model that accounts for something this massive forming this early. Make it consistent with everything else we know about black holes, star formation, galaxy evolution, and the early universe, and do it without invoking magic or miracles or physics that has never been observed. That is the challenge, and we are not there yet. Priyamvada Natarajan has spent her career thinking about these questions. How do black holes form? How do they grow? Why do we see such massive black holes so early in the universe? In a series of papers published over the last decade, she and her collaborators have argued that direct collapse is the only viable explanation for the most massive black holes in the early universe. Not because the other mechanisms are impossible, but because they are too slow. The universe did not give them enough time. If you want a billion solar mass black hole sitting at a redshift of 7, you need a seed that starts at a few 100,000 solar masses or more. Stellar remnants start at a few dozen solar masses. The gap is too large. Direct collapse is the only mechanism that provides seeds heavy enough to reach the observed masses in the time available. And if direct collapse works for those early quasars, it almost certainly works for Phoenix A star. The black hole is later, sitting at a redshift of less than 1, but the same logic applies. Something this massive needs a head start, and direct collapse gives it that head start. The observational challenge is not going away. Even with Webb, even with the next generation of telescopes currently being planned, finding a direct collapse black hole in the act of forming is going to be extraordinarily difficult. The events are rare, the timescales are short, and the signatures are faint. But there are indirect ways to test the hypothesis. If direct collapse black holes formed in large numbers in the early universe, They should have left an imprint on the overall population of supermassive black holes we see today. Specifically, the mass distribution should be skewed toward heavier black holes compared to what you would expect from stellar remnant seeds. The earliest black holes should be systematically more massive, and that is exactly what we are starting to see. Webb has found multiple galaxies in the early universe with black holes that appear to be too heavy for their host galaxies, black holes that weigh a significant fraction of the total stellar mass. In normal galaxies, the black hole weighs about 0.1% of the stellar mass. In these early galaxies, the black hole can be 1% or more. That is consistent with a scenario where the black hole formed early, from a massive seed, and the galaxy built up around it later. It is not proof, but it is suggestive, and as more data comes in, the picture is getting clearer. Phoenix A* is not just the largest black hole we have ever found. It is the culmination of a process that started billions of years ago with a seed we have never seen. That seed, whatever it was, grew over 8 billion years into the monster sitting at the center of the Phoenix cluster today. The seed is the key, the missing piece, the starting point that determines everything that comes after. And until we find a direct collapse black hole, or an intermediate mass black hole, or definitive evidence of primordial black holes, we are left guessing. Educated guesses, informed by simulations and observations and decades of theoretical work, but guesses nonetheless. The seed is hiding somewhere in the first few 100 million years of cosmic history, buried in an era so distant and so faint that even our best telescopes struggle to see it. And the only way we know it exists at all is because of what it became. A black hole weighing 100 billion times the mass of our Sun. A shadow 590 billion kilometers across. A region of space-time so warped that it has consumed more matter than most galaxies will ever hold. That is the legacy of the seed, and until we find it, Phoenix A* will remain a monument to a process we understand in theory but have never witnessed in practice. A giant built on foundations we can infer but cannot see. A structure so massive that its very existence forces us to admit that somewhere, somehow, the early universe was doing something we have not figured out yet. The seed is hiding somewhere in the first few 100 million years of cosmic history, buried in an era so distant and so faint that even our best telescopes struggle to see it, and the only way we know it exists at all is because of what it became. A black hole weighing 100 billion times the mass of our Sun. A shadow 590 billion kilometers across. A region of space-time so warped that it has consumed more matter than most galaxies will ever hold. That is the legacy of the seed, and until we find it, Phoenix A* will remain a monument to a process we understand in theory but have never witnessed in practice. A giant built on foundations we can infer but cannot see. A structure so massive that its very existence forces us to admit that somewhere, somehow, the early universe was doing something we have not figured out yet. Which brings us to the deeper question, not just how Phoenix A* formed, but what it means. What does the existence of a 100 billion solar mass black hole tell us about the universe we live in? What boundaries does it break? What assumptions does it force us to abandon? Because Phoenix A* is not just a record holder, it is not just an impressive number on a spreadsheet. It is a violation, a cosmic outlier that sits outside the neat boxes we have spent decades constructing. And every time we find an object like this, an object that refuses to behave the way our models say it should, we are forced to make a choice. Either the object is wrong, which it cannot be because it exists, or the models are incomplete. And if the models are incomplete, we need to figure out what we missed. What piece of physics, what mechanism, what process did we fail to account for that allowed the universe to build something this extreme? Let us start with the ceiling problem. For years, astronomers believed there was a natural upper limit to how massive a black hole could become. Not a hard limit written into the laws of physics, but a practical one imposed by the environment. The Eddington limit sets a maximum feeding rate. Black holes that try to eat faster than that limit blow away their own food with radiation pressure. That means black hole growth is self-regulating. The bigger the black hole gets, the more it eats, the more radiation it produces, and eventually it reaches a point where it cannot grow any faster. Add to that the finite amount of gas available in any given galaxy, the fact that galaxies stop forming stars after a certain point, and the observation that most supermassive black holes appear to go dormant after a few billion years of active feeding, and you end up with a picture where black holes naturally top out somewhere in the tens of billions of solar masses. 50 billion was the number that kept getting thrown around, not because anyone had proven that was the limit, but because nothing we had observed exceeded it by much. TON 618, at 66 billion solar masses, was already pushing the boundary. And then Phoenix A* showed up at 100 billion and broke the ceiling entirely. Priyamvada Natarajan, who has been tracking this problem for her entire career, put it plainly in a 2024 interview. Research indicates ultramassive black holes may have a growth limit of 100 billion solar masses, not 50 billion, 100 billion. Phoenix A* is not just heavy, it is sitting at the theoretical maximum. The absolute upper edge of what a black hole can become before some other mechanism, something we do not fully understand yet, stops the growth. Maybe it is feedback. Maybe at 100 billion solar masses, the black hole becomes so luminous, so energetically dominant, that it blows away every gas cloud within a billion light-years and starves itself. Maybe it is dynamical friction. Maybe black holes, this massive, start interacting with the dark matter halos around them in ways that eject them from their host galaxies. Maybe it is something else entirely, we do not know. But Phoenix A* suggests that whatever the mechanism is, it kicks in somewhere around 100 billion solar masses, and that is the new ceiling, not because we have proven it theoretically, because the universe showed us. That changes the map. For decades, we have been building models of how galaxies and black holes grow together, how they influence each other, how feedback from the black hole regulates star formation and prevents galaxies from overproducing stars. Those models were calibrated using black holes in the few million to few billion solar mass range. Sagittarius A* in the Milky Way, the black hole in M87, the quasars in the distant universe. All of them fit comfortably within the framework. None of them were extreme enough to break anything. Phoenix A* is extreme enough. It sits so far outside the normal distribution that it forces us to ask whether the framework itself is missing something. Not whether it is wrong, whether it is incomplete. Whether there are regimes, environments, epochs in cosmic history where black holes behave differently than our models predict. And if those regimes exist, we need to find them, map them, figure out what makes them special. One of the biggest mysteries Phoenix A* presents is its relationship with the galaxy around it. In a normal galaxy, the central black hole weighs about 0.1% of the total stellar mass. The Milky Way has roughly 200 billion stars. Its central black hole weighs 4 million solar masses. Do the math, and the black hole is a rounding error, a tiny fraction of the galaxy's total mass. Even in the most massive galaxies we know, the ones sitting at the centers of galaxy clusters, the black hole typically weighs less than 1% of the stellar mass. That ratio, the black hole mass to stellar mass ratio, has been remarkably consistent across thousands of galaxies. It is one of the tightest correlations in all of astrophysics. And it tells us something fundamental about how black holes and galaxies grow together. They are linked. When the galaxy grows, the black hole grows. When the black hole grows, it regulates the galaxy's growth through feedback. The two systems are coupled, co-evolving, keeping pace with each other over billions of years. Phoenix A star does not follow that script. The black hole weighs 100 billion solar masses. The galaxy it sits in, the central galaxy of the Phoenix cluster, weighs somewhere in the range of a few 100 billion solar masses in stars. The exact number is hard to pin down because the galaxy is so large and so diffuse that defining its edges is tricky. But even with generous estimates, the black hole represents a significant fraction of the galaxy's total stellar mass. Not 0.1%, not 1%, closer to 50%. Half the mass of the galaxy is sitting inside the black hole. That is not a correlation, that is a takeover. The black hole is not a minor component of the system, it is the system. The galaxy has become an accessory to the black hole rather than the other way around. How does that happen? How does a black hole grow so massive that it rivals the galaxy that hosts it? One possibility is that the galaxy stopped forming stars early. Maybe it exhausted its gas supply billions of years ago, and the stars we see today are just the remnants of an ancient burst of star formation that happened when the universe was young. If the galaxy stopped growing while the black hole kept feeding, the black hole could catch up, but that does not match what we observe. The Phoenix cluster is forming stars, a lot of stars, 1,000 solar masses per year. That is not a dead galaxy. That is a galaxy in the middle of a growth spurt. The stars are young, the gas is abundant, the system is active, and yet the black hole is still enormous relative to the stellar population, which means either the black hole grew faster than the galaxy, or the galaxy has been unusually inefficient at turning gas into stars, or both. The feedback mechanism is supposed to prevent this. In a normal system, the black hole grows by eating gas. As it eats, it produces radiation and jets that heat the surrounding gas and prevent it from collapsing into stars. That limits how much gas is available to form new stars, but it also limits how much gas is available to feed the black hole. The system self-regulates. The black hole and the galaxy grow together, maintaining a rough balance. But in the Phoenix cluster, that balance has broken down. The black hole is growing, the stars are forming, and the feedback mechanism that is supposed to stop both processes from running away is either not working or not working fast enough. The black hole is eating 60 solar masses per year. The galaxy is forming 1,000 solar masses per year. The total inflow of gas is more than 1,000 solar masses per year. Only 6% of that gas is making it to the black hole. The rest is bypassing it entirely and forming stars. That is the opposite of what feedback is supposed to do. Instead of the black hole shutting down star formation, the star formation is overwhelming the black hole. This is the paradox that keeps coming back. Phoenix, a star, is the largest black hole we have ever found, and it is failing to do the one job every supermassive black hole is supposed to do: regulate its environment. The galaxy is thriving, the cluster is glowing with the light of newborn stars, and the black hole is sitting there, feeding, growing, and watching it all happen. Either the black hole is not powerful enough to stop the inflow, which seems absurd given its size, or the environment is so gas-rich that even a 100 billion solar mass black hole cannot keep up. Both options suggest that our understanding of feedback is incomplete, that there are conditions, environments, regimes where feedback does not work the way we think it should. And Phoenix, a star, is showing us one of those regimes in action. The Eddington limit is another piece of the puzzle that does not quite fit. Phoenix, a star, is feeding at 60 solar masses per year. That sounds like a lot, and it is. But for a black hole this massive, 60 solar masses per year, is actually below the Eddington limit. The Eddington limit for a 100 billion solar mass black hole is roughly 10,000 solar masses per year. Phoenix, a star, is feeding at less than 1% of its maximum rate. That tells us the black hole is not being starved. It is not running out of food. The gas is there. The cooling flow is pouring it inward, but the black hole is only eating a tiny fraction of what is available. The rest is forming stars. Why? If the gas is falling inward, if it is reaching the core of the cluster, why is only a small fraction making it to the black hole? What is stopping the rest? One hypothesis is angular momentum. Gas falling toward a black hole does not fall straight in. It has rotation, spin, angular momentum, and angular momentum resists inward motion. The gas has to lose angular momentum before it can cross the event horizon. Normally, that happens through friction in the accretion disk. Gas particles collide, transfer energy. Some of them lose angular momentum and spiral inward. Others gain angular momentum and move outward. The process is efficient but not perfect. Most of the gas eventually makes it to the black hole, but in a system like the Phoenix cluster, where the inflow rate is so high, the accretion disk might not be able to process all the gas fast enough. Some of it piles up, some of it gets flung outward by magnetic fields or radiation pressure, and some of it, a lot of it, never makes it to the black hole at all. It stays in the core of the cluster, cools, condenses, and forms stars. The black hole is not eating slowly because it wants to. It is eating slowly because the delivery system is inefficient. The gas is there, but it cannot get in fast enough. That is speculative, but it fits the observations, and it suggests that the relationship between black holes and their environments is more complicated than a simple feedback loop. The black hole is not just a thermostat that heats the gas and shuts down cooling. It is a dynamic system that interacts with the gas in ways that depend on the inflow rate, the angular momentum, the magnetic fields, the radiation pressure, and a dozen other factors we are only beginning to understand. In some environments, feedback dominates and star formation is quenched. In others, like the Phoenix cluster, the inflow overwhelms the feedback and star formation runs wild. Phoenix A star is not breaking the rules. It is showing us that the rules are more flexible than we thought, that there are edge cases, outliers, extremes where the standard picture does not apply. And if we want to understand how black holes really work, how they really interact with their environments, we need to study those edge cases. We need to find more Phoenix A stars, more systems where the black hole is doing something unexpected, because those are the systems that teach us what we are missing. The implications for cosmology are larger than just black holes. Phoenix, a star, sits 5.7 billion light-years away. That means we are seeing it as it existed 5.7 billion years ago, when the universe was roughly 8 billion years old. By that time, the universe had settled into a relatively mature state. The era of rapid galaxy formation was over. Most of the stars in the universe had already been born. Most of the supermassive black holes had already grown to their current sizes. The universe was quieter, calmer, more orderly than it had been in its youth. And yet there was Phoenix A star, a black hole weighing 100 billion solar masses, sitting in a cluster forming 1,000 stars per year, an environment that looked more like the early universe than the late universe, a pocket of chaos in an otherwise mature cosmos that tells us something about how structure forms. In the standard picture, The universe starts out smooth and gradually gets lumpier. Small fluctuations in density grow under gravity, pulling matter together into clumps. Those clumps become stars, galaxies, clusters. Over time, the lumps get bigger and the universe becomes more structured. But the process is supposed to slow down. As the universe expands, the density drops, the gravitational pull weakens, and the rate of structure formation decreases. By 8 billion years after the Big Bang, most of the action is over. The universe is coasting. Structures that formed early are evolving, merging, rearranging, but new structures are not forming at the same furious rate they did in the first few billion years. Phoenix A* challenges that picture. It suggests that in some regions, in some environments, structure formation did not slow down. It kept going. Gas kept flowing inward. Stars kept forming. Black holes kept growing. And those regions produced objects that should not exist if the universe had really settled into the mature phase we think it did. The Phoenix cluster is one of the most massive galaxy clusters in the universe. It is also one of the most X-ray-luminous. The hot gas in the cluster is glowing so brightly in X-rays that it outshines most other clusters by a factor of 7. That extreme X-ray luminosity is a sign of extreme gravitational energy. The cluster is massive, dense, and actively pulling in matter from its surroundings. It is not a relic. It is not a fossil. It is a living, growing structure. And at its heart sits Phoenix A*, feeding on the inflow, growing at 60 solar masses per year, and presiding over a galaxy that is forming 1,000 stars per year. This is not what a mature universe is supposed to look like. This is what the early universe looked like. Violent, chaotic, building structures at a rate that defies the standard timeline. If the Phoenix cluster is not unique, if there are other clusters out there with similar properties, similar black holes, similar star formation rates, then the standard picture of cosmic evolution is incomplete. It accounts for the average, the typical, the well-behaved systems that make up the bulk of the universe, but it does not account for the extremes, the outliers, the systems that refuse to follow the script. And if those systems are more common than we thought, if they represent a significant fraction of the total population, then we need to revise the models, not because they are wrong, because they are incomplete. They describe the average but miss the tails of the distribution. And the tails, the extremes, the outliers, are where the most interesting physics happens. That is where the universe shows us what it is really capable of. That is where we learn. The search for similar objects is ongoing. Astronomers are scanning the sky with X-ray telescopes, looking for clusters with the same extreme luminosity as the Phoenix cluster. They are using infrared telescopes to search for galaxies with unusually high star formation rates. They are analyzing gravitational lensing data to identify regions where the mass distribution is unusually concentrated. And they are finding candidates, not many, but enough to suggest that Phoenix A* is not alone. There are other black holes out there in the tens of billions of solar masses, maybe even other black holes in the 100 billion solar mass range. We just have not confirmed them yet. The observations are difficult, the objects are distant, the measurements are uncertain, but the hints are there. And as our instruments improve, as our surveys get deeper, as we develop better techniques for measuring black hole masses at extreme distances, we will find more. The question is not whether more Phoenix A* exist. The question is how many, and what that number tells us about the universe. One of the most exciting prospects is the next generation of gravitational wave detectors. The Laser Interferometer Space Antenna, LISA, is scheduled to launch in the 2030s. Unlike LIGO, which detects gravitational waves from stellar mass black hole mergers, LISA will be sensitive to waves from supermassive black hole mergers. When two black holes in the tens of billions of solar masses collide, they produce gravitational waves with wavelengths so long that they can only be detected from space. LISA will be able to hear those collisions from across the universe. And if Phoenix A star grew primarily through mergers, if it is the product of dozens or hundreds of black hole collisions over billions of years, then there should be other black holes out there that are in the process of merging right now. LISA will detect them. It will measure their masses, their spins, their distances, and it will tell us how common these extreme mergers are, how often they happen, how much they contribute to the growth of the largest black holes in the universe. That data will be transformative. It will turn black hole formation from a theoretical puzzle into an observational science. Phoenix A star also raises questions about the ultimate fate of black holes. If 100 billion solar masses is the maximum, if that is the ceiling, then what happens when a black hole reaches that mass? Does it stop growing? Does it get ejected from its host galaxy? Does it merge with another black hole and exceed the limit? Or does some other process prevent that from happening? We do not know, and we will not know until we find more black holes at or near that mass. Phoenix A star might be the largest black hole the universe can make, or it might just be the largest one we have found so far. The difference matters. If it is the largest possible, that tells us something fundamental about the limits of structure formation, about the maximum density, the maximum mass concentration, the maximum curvature of spacetime that the universe allows. If it is just the largest we have found, that tells us we have not been looking hard enough, that there are even more extreme objects out there waiting to be discovered. Either way, Phoenix A star is a benchmark, a reference point, the current record holder in a contest that has been running for 13.8 billion years. There is also the question of what happens to the galaxy. Right now, the Phoenix cluster is forming 1,000 stars per year. At that rate, the cluster will exhaust its cold gas supply in a few 100 million years, maybe less. When that happens, the star formation will shut down, the galaxy will stop growing, and Phoenix A star will still be there, still feeding, still growing, but more slowly. Without the continuous inflow of gas, the accretion rate will drop. The black hole will go quiet. It will become a dormant giant, sitting at the center of a red and dead galaxy, radiating almost nothing, invisible except for its gravitational influence. That is the fate of most supermassive black holes. They grow rapidly for a few billion years, then go dormant and spend the rest of eternity coasting. Phoenix A star will likely follow the same path, but it will do so from a higher starting point. It will shut down at 100 billion solar masses, and once it does, it will be effectively frozen, growing only through the occasional collision with another black hole or the rare infile of a star that wanders too close. For all practical purposes, 100 billion solar masses will be its final mass, the end state, the configuration it will maintain for the rest of the universe's history. That history is long, unimaginably long. In a few trillion years, the last stars in the universe will burn out, the cosmos will go dark, galaxies will drift apart, carried by the expansion of space, until they are so far apart that light from one galaxy can never reach another. The universe will be cold, empty, and silent, and Phoenix A star will still be there, a black hole weighing 100 billion times the mass of our Sun, sitting in the darkness, emitting nothing, growing imperceptibly slowly through the occasional capture of a stray photon from the cosmic microwave background. Over timescales that make billions of years look like seconds, Phoenix A star will evaporate. Hawking radiation, the faint glow of particles that black holes emit due to quantum effects near the event horizon, will slowly carry away its mass. The process will take 10 to the 100 power years, a 1 followed by 100 zeros, a timescale so long that the current age of the universe, 13.8 billion years, is a rounding error. But eventually the black hole will shrink. Its event horizon will contract. Its mass will decrease. And at some point, far beyond the end of everything we recognize as the universe, Phoenix A star will evaporate completely. The last photon will escape. The last particle will be emitted, and the black hole will be gone, not collapsed, not destroyed, just dispersed, returned to the quantum foam from which it came. That is the ultimate fate of every black hole, even the largest ones, even Phoenix A star. But we are not there yet. Right now, Phoenix A star is alive, active, growing, and every observation we make, every measurement we take, every data point we collect, brings us closer to understanding how it came to be. The James Webb Space Telescope is continuing to observe the Phoenix cluster. The Atacama Large Millimeter Array is mapping the cold gas in the core. The Chandra X Ray Observatory is monitoring the hot gas and the jets. And next-generation instruments, telescopes that have not been built yet, will push even deeper. They will resolve the structure of the accretion disk. They will measure the spin of the black hole. They will detect the gravitational waves from mergers involving black holes this massive. And with each new piece of data, the picture will get clearer. Not complete, probably never complete, but clearer. Phoenix A star is not just a black hole. It is a question, a challenge, a boundary marker that tells us how far the universe can push the limits of gravity, density, and mass. It is a violation of the expectations we built from smaller, tamer systems. It is a reminder that the universe is under no obligation to make sense to us. That our models, no matter how elegant, no matter how successful, are approximations, useful approximations, but approximations nonetheless. And when we find an object that breaks those approximations, we have two choices: ignore it, which is intellectually dishonest, or confront it, study it, figure out what it is trying to teach us. Phoenix A star is teaching us that black holes can grow larger than we thought. That feedback is not as effective as we assumed, that the early universe was capable of building structures we are only now beginning to find, that the ceiling we thought was solid is actually just a suggestion, and that the universe, given the right conditions, will ignore our suggestions and build whatever it wants. The largest black hole in the known universe is sitting 5.7 billion light-years away. It weighs 100 billion times the mass of our Sun. It has an event horizon you could fit the solar system inside. It is feeding at 60 solar masses per year. It is presiding over a galaxy cluster that is forming 1,000 stars per year. It formed from a seed we have never seen, through mechanisms we only partially understand, in an environment that refuses to behave the way our models predict. And it exists. It is real. It is out there right now, curving space-time, swallowing matter, growing steadily, and rewriting the rules as it goes. That is Phoenix A star, not the end of the story, the beginning of a new chapter. A chapter where the universe shows us just how extreme things can get when gravity, time, and matter are given billions of years to do whatever they want. And the answer, apparently, is this: 100 billion solar masses, a shadow that stretches across thousands of astronomical units, a black hole so massive that it defines the upper limit of what a black hole can be, not because the math says so, because the universe built one and stopped. Phoenix A star is not just the largest black hole we have ever found. It might be the largest black hole that can exist. And if that is true, if 100 billion solar masses is the ceiling, then Phoenix A star is not an outlier. It is the finish line, the final boss, the ultimate expression of what happens when a black hole has everything it needs and all the time in the world to grow. It grew, it reached the top. And now it sits there, at the edge of possibility, daring us to explain how it got there. We are working on it. The data is coming in, the models are being refined, the observations are getting sharper, and one day, maybe soon, we will have an answer. But for now, Phoenix A star remains what it has always been: a mystery, a monument, a black hole so large that it broke physics and forced us to admit that the universe is stranger, more violent, and more capable than we ever imagined. And it is still out there, growing, feeding, waiting. 100 billion suns, all of them gone, all of them swallowed, all of them erased. And the black hole does not care. It never has. It never will. It is just a region of curved space-time doing what curved space-time does: existing, growing, and redefining what is possible one solar mass at a time. Phoenix, a star, is not the end of the story. It is the edge of what we can see, the boundary of what we have found so far. And boundaries in science are not walls, they are invitations. Every record that gets broken, every object that refuses to fit the models, every measurement that lands outside the predicted range, is the universe tapping us on the shoulder and saying, "Look closer, dig deeper. You are missing something." We built models that said black holes should top out at 50 billion solar masses. Phoenix A star weighs 100 billion. We built theories that said feedback should regulate star formation in massive clusters. Phoenix A star is sitting in a cluster forming 1,000 stars per year. We calculated timelines that barely allowed for the growth of the earliest supermassive black holes. Phoenix, a star formed in 8 billion years from a seed we have never seen. Every rule we thought was solid has flexed. Every ceiling we thought was real has lifted. And the black hole is still there, still growing, still feeding, still defying us to explain it. What Phoenix, a star, really represents is not an answer. It is a question we have not finished asking. How extreme can the universe get? How massive can a black hole grow before something, some mechanism we do not yet understand, stops it? How many more Phoenix A stars are out there, hidden in distant clusters, waiting for our instruments to improve enough to find them? And what does it mean that the largest object we have ever discovered, an object that weighs more than most galaxies, is still just a snapshot? A freeze frame of a process that has been running for billions of years and will keep